Okay, good morning, everyone. Welcome to the Parallel and Distributed Computing in Python with Dask tutorial. I'm going to be the host for this session, and presenting are James Bourbeau, Mike, his name last time I forgot, and Darhaz Pothina. So I'll be the host. I'll be monitoring the questions section. So if you have a question, we prefer that you ask that question in the Ask a Question using that Ask a Question button. You can also ask a question in the chat, and I can promote it over to the Ask a Question section. And then I'll be marking when the presenters have answered questions, and then moving them into the answered questions column. And then we please ask that everybody follow the code of conduct. And if anybody doesn't, then I have the power to remove them from the room. So please don't make me use that power. Okay, so with that, I'll introduce James Bourbeau, who will be the first presenter, and I will mute myself. And Mike, I'm going to take you out of the room for now. Okay. So closing that, and then.
Great. I'll go ahead and share my screen. All right. So now everyone should be able to see my screen. Great. So just to confirm, can people, I guess I can only hear Darhaz. Darhaz, so you can see the screen. Everything's okay?
Yes.
Great. I'm going to maybe increase the font size to here. Hopefully this is okay for everyone. I guess Darhaz, I can hear you. Does this look reasonable on your screen at least?
This looks reasonable on my screen, and it looks like in the comments, people are saying it looks good.
Awesome. Okay. Thanks for checking. All right. Welcome, everyone. Thanks for attending the Dask tutorial session here at SciPy 2020 today. We appreciate the, both your time and your attention. My name is James Bourbeau. I am one of the maintainers for Dask. I'm also a software engineer at Coiled Computing. I'm also joined by my two co-instructors today, Darhaz and Mike, and just to minimize the number of times we invite people on stage, we'll have them introduce themselves when we get to their portions of the tutorial. From a really like high vantage point, Dask is a Python library for parallel and distributed computing in Python that scales the existing Python ecosystem. So a lot of the Dask code that you'll end up writing looks very familiar to maybe NumPy or Pandas code that you are already used to writing. The idea is that the Dask variants will just scale to larger data sets that you wouldn't be able to handle using NumPy and Pandas. So this tutorial is targeted at just new users to Dask, so no prior Dask knowledge is assumed. We are sort of hoping you're familiar with things like NumPy and Pandas, but you don't have to have seen Dask before to get something out of this tutorial. So Dask, broadly speaking, consists of sort of two, you can view Dask as having sort of two portions, a collections portion, which is for creating task graphs or setting up computations. So there are different interfaces for this. There are Dask arrays and Dask data frames, for example. There are other interfaces as well, but Dask arrays mirror NumPy ND arrays. Dask data frames mirror Pandas data frames. And there's also other interfaces that we'll talk about. For instance, the first one we'll talk about is Dask Delayed, which is used for creating custom workflows. So these collections generally are for constructing, setting up a computation. That's one portion of Dask. The other portion are schedulers, which actually execute those computations potentially in parallel. And we will talk about those later in the tutorial. Excuse me. If you want some examples of Dask, like in the wild, Dask being used in the wild, I recommend checking out this use cases link here. So you can see that real quick. Yeah, so there are several sort of different testimonials about Dask being used in the real world. For today, the tutorial materials are available at this GitHub repository, so github.com/dask/dask-tutorial. That's here. So there are a few different ways to set things up for the tutorial. You only have to do one of these things. So there are three different options here, A, B, and C. You only have to choose one of those options. You don't have to do all three. The preferred method is to use our this Conda environment file to create a new Conda environment, activate it, and then install the Jupyter Lab extensions. There is also options B and C as well. And those are for setting up the tutorial and installing all the packages locally. If you would prefer to not do that and avoid any local setup, towards the top of the README, there's this launch binder button that you can click, and that will, thanks to the binder team, that will launch a Jupyter Lab session for you. It has everything already set up. It has all the notebooks for the tutorial, as well as all the necessary packages already installed, ready for you to go. So just wanted to give a big shout out and thanks to the entire binder team for providing this infrastructure for us. So that's it for the setup. There are some additional links here that are relevant. So we link here to the Dask documentation. We also link to the Dask source code in GitHub. And the Dask community also maintains a blog that you can go check out to see sort of what the current activities are happening in the ecosystem. Then here are a couple links for asking for help. So you can use the Dask tag on Stack Overflow if you have any usage questions. So how do I do this? What, for instance, would be an appropriate question for Stack Overflow. If instead you have a bug report or perhaps a feature request, we would ask that you open up a new issue on the Dask GitHub issue tracker for bug reports and feature requests. There's some additional information here about the structure for the tutorial. The tutorial takes place in a series of Jupyter notebooks. So yeah, we don't need to go over all this material other than, I guess the main thing is if you're totally new to Jupyter, when you're in the different notebook cells, as we'll see, hit Shift and Enter to execute the contents of the cell. So one thing I did want to point out is the exercises. Rather, throughout the course of the tutorial, there will be a series of exercises. There'll be some prompt here telling you sort of what the exercise, what the goal of the exercise is. Then you'll see a code cell here that typically will have some commented out portion, and you're supposed to then put your solution for the exercise into this cell. So, for instance, here it's saying print the text "Hello World," so we would do print "Hello World." And then to execute cells again, Shift Enter. There we go, and we see the output. And then beneath this cell where you've executed your, where you've put in your solution for the exercise, there will be another cell with just three dots here, like an ellipses. If you click that, that will then reveal a solution for that exercise. So you can use that to then compare your solution to the exercise against a solution we've already prepared, or if you get stuck in an exercise and need some help, you can then consult the answer. Yeah, that is it for the overview. If you have, just to kind of reiterate the administrative point, if you have any questions, ask them in. Be sure to ask them in Crowdcast, and if they're sort of require a more detailed answer, then they'll be moved to the Slack channel, the Dask tutorial. I think it's tutorial_Dask Slack channel. Okay. So, any questions at this point? I'll maybe go over to the questions. Okay. So, does Dask use MPI internally? We can answer that at another time. Okay. So hopefully at this point, everyone is set up. If you're not set up at this point, I recommend using Binder to avoid having to do any local setup. So just go to the tutorial and click this Launch Binder button. Okay, so the first notebook we're going to talk about today we're going to go through is this 01 underscore Dask Delayed notebook. So, as you might expect, in this notebook, we'll be covering the Dask Delayed interface. So this is a way to use Dask to delay function evaluation. This is commonly used to parallelize existing workflows. So if you have a code base that is running synchronously with no parallelization, using Dask Delayed is a common way to then incorporate parallelization. Additionally, it's also used to build really complex user workflows as well that don't fit nicely into like array and DataFrame workloads. So here are some relevant links for Dask Delayed. So there's Dask Delayed specific documentation. There's also a nice screencast on YouTube that walks you through some of the delayed basics. We also link to the delayed API documentation. There are delayed examples, and in particular, I wanted to point out this last link, the delayed best practices. This contains, a series of best practices for using Dask Delayed, as well as solutions for some like common problems that users will run into using Delayed. In particular, people who are new to using Dask Delayed. So, highly recommend checking out the best practices page. So here we have, we're basically going to ignore this for now. We're going to ignore it for now and come back to this later. So Dask has several ways in which you can create, in which you can execute things. This way here, we're using a distributed cluster. We will come back to this later in the tutorial. So for now, ignore this. We will just execute this cell and come back to this later. So let's set up the basics here. So we here have defined two functions, an increment function and an add function. The increment function just takes an input and returns that plus one. The add function it takes two inputs and adds them together and returns that. And they both sleep for 1 second here. This is to simulate some kind of work happening. You can imagine in your actual workflow, this might be load data, this might be process data, for instance. So we'll define those two increment functions, and then we will run increment 1, assign that to X, increment 2, assign that to Y, and then add those together to get an output. So here you'll see I'm using the Jupyter time magic. That's what the % time does. What that does is it spits out this extra output here. So what this tells us is that I went ahead and executed this cell, and it took 3 seconds for the contents of that cell to execute. So executing this cell took 3 seconds in total, 3.10 seconds in total. We see, however, here that there is some opportunity for parallelization. For instance, add here takes in two inputs, X and Y. But then if we look at X and Y, we can see that they are completely independent. So they don't depend on one another. We can run those in theory in parallel. So let's do that using Dask Delayed. So delayed object, or the delayed function, lives inside Dask. So you can from Dask import delayed. And then how you actually use the delayed decorator is you wrap functions with this delayed decorator. So if we compare this cell to the cell just up here, you can see the only difference is that I'm instead of calling ink on one, I'm first wrapping ink in this delayed decorator, and then that's it. I'm doing the same down here with ink. I'm doing the same here with add. So let's go ahead and execute that cell. So that ran much faster. That took 1.46 milliseconds, whereas before it took 3 seconds. That's because this didn't actually do the computation. This didn't actually really run these increment and add functions. What it did instead was it set up a computation. It built a task graph for what you would want to do to compute these different variables, but didn't actually run the computation. To actually run the computation, you can call compute on these objects. So here's where the actual computation happens. And notice that took 2 seconds. So faster than before. Before it took 3 seconds. Now it took 2 seconds. So let's sort of unpack what just happened there a little bit more. So up here, I've defined Z to be delayed add, and then I'm going to pass into that X and Y. So what that returns is a delayed object. So whenever you wrap functions with the delayed decorator, they then will, when those functions are then called, they will then return delayed objects. As I said before, these delayed objects basically keep track of the function that is being executed and the inputs to that function. They don't actually perform that, they don't actually like evaluate that function with those inputs. They just keep track of them. And then you can pass delayed objects to other functions that will then build up the computation themselves. So delayed objects, like all Dask collections, have a visualize method that you can use to visualize the underlying computation that's being built up for that object. So for the Z delayed object here, we can visualize it and we get this graph here. So here we can see our 2 increment calls. So to kind of interpret this graph, the circles here represent function calls, and like the name of the function should be inside the circle. So these are our 2 increment calls here. They both produce output that are represented by these 2 boxes here. Then we take those outputs and pass them to the add function. And the output of that is this box here, and that's sort of our final output. So when we call z.compute, we then go ahead and actually compute all of these function calls, and what is returned is this final output here. So what we can see is that these 2 increment functions could, in theory, be called in parallel because they're totally independent. So some questions to ask about our workflow. So before, when we called compute without Dask, it took 3 seconds to run. With Dask delayed, it took 2 seconds to run. Why weren't we able to parallelize down to 1 second? That's because each of these function calls to these inks and this add function each sleep for 1 second. So like the maximum amount of time would be 3 seconds, which is what we're getting in the synchronous mode without Dask. However, there is this dependency structure between the add function and the outputs from the 2 increment functions. So we can't run add in parallel with these 2 increments. We have to run these increments. We can run those separately, but then we have to wait for both those to finish, and then we can run the add. So these sleep at the same time for 1 second, and then the add sleeps for 1 second. That's how we're getting the 2 seconds instead of 1. So that's sort of the basics of Dask delayed. The idea is to wrap function calls in Dask delayed. They will then become lazily evaluated delayed objects that you can use to build up computations in a very similar way that you would do without using Dask delayed. So the code should look very similar. You'll just kind of pepper in a few Dask delayed decorators here and there. So we're now at our first exercise, parallelizing a for loop. This is a very common problem that people run into, is they have some for loop that could be parallelized. Each iteration, each loop in the for loop is totally independent of the other, of like a subsequent iteration in the loop. And so in theory, you can run those in parallel. So here we have some data. We have a list, 1 up to 8. And here is some sequential code. I'll go ahead and run this. You see we have a results empty list. We then loop through our data. We then pass each item as we're looping through the data. We then pass that through the increment function, which sleeps for 1 second to get y. And then we append that to our results list, and then we sum up all the results in the end. So the result we get out in the end is 44. That's like the sum of all these results. And it takes 8 seconds to actually complete, to run this code. So for the first exercise, what we want to do is use Dask delayed to parallelize this example here. So you can go ahead and do that here. So we'll pause for a few minutes here to allow time to go ahead and do that, and then we'll come back and talk about the solution.
Do we want to look at some of the questions? It looks like we have a little backlog of questions.
That's what I'm doing now. So does Dask use MPI internally? Dask, you can deploy Dask using MPI. Dask does not use MPI internally, although it integrates well with MPI. There's a Dask MPI project on GitHub if you're interested in looking at how you can run Dask on MPI. Yeah, great question. What is a task graph? So a task graph is the computation that is built up. So maybe if I share my screen again. So this picture here is a visualization of a task graph. So what a task graph is a structure that contains, like what a task is a function that you want to call and the inputs to that function. That's what a task is. And a task graph is like a collection of those functions that you want to call that encodes their dependencies. So for instance, here, we're saying we want to call this increment function with some inputs. I think we're calling one of them is incrementing 1 as the input, and the other one is the inc function with 2 as the input. And then we want to add them together. The outputs of inc1 and inc2, we want to then use as inputs to the add function. So a task graph is a collection of tasks, which are functions and inputs to those functions, and then dependencies. So you can see here we're saying call inc, get an output, call inc, get an output, take those outputs, pass them to the add function, then the actual output for our computation, the output from this task graph that we want is the output from that add function. So that's what a task graph is. It's a structure that sets up a computation. It doesn't actually perform the computation, but it sets up a graph structure that allows us to later, when we call compute on in this case, the Dask delayed object or other Dask collections, we can call compute, then we'll actually execute the task graph to get our actual answer out.
So answering the next question, we are not building the task graph. We are just making different functions delayed and putting them together. And in the background, Dask is building the task graph for us. And later we'll get to how the Dask decides where to move those computations and how to run them. Lazily evaluated. What this means is Dask does not actually compute anything until it needs it. So it just builds up the task graph, but you don't actually have the answer until you explicitly tell it to compute the answer, or it hits a particular location where it can't move forward without computing the answer.
All right, I'm going to go ahead and share my screen again, and then we can, hopefully at this point, people will have a solution for the exercise. So, and then, yeah, then I'll answer. I saw one other question about decorators, which I'll answer next. So here is a solution for this problem. So we can see the original code up here and the Dask delayed version down here. So what you'll notice is that it looks very similar. The only difference is that here we're delaying the increment function, whereas before we were just calling the increment function directly. And then we're delaying sum here, and at the end we're calling compute. So that's really the name of the game here using Dask delayed, is to delay functions, delay expensive functions by applying the delayed decorator. And then the only extra step you have to do is, because, as we've mentioned, Dask is lazily evaluated, you then have to call compute at the end to actually get your result out. So here we can go ahead and run this code. Let me actually add the time magic here. Yep. So we ran the code here and it took 1 second. So, and keep in mind, I am computing the result here. So I'm not just setting up the graph and doing nothing else. I'm actually computing the results. So it took 8 seconds before. I have 8 cores on this computer, right? So it takes 1 second here because I'm able to run 8 different things in parallel. I did see a question in the question section about using decorators. So here in this tutorial, we're delaying everything explicitly, sort of using this notation. We're replacing inc with delayed inc. Oftentimes, so this is nice in a tutorial setting because it's very explicit about what is being delayed where. Oftentimes you'll see people use the decorator syntax instead. So you'll have a function like this, increment x, return x plus 1. Often what you'll see people do, instead of sort of where the function is used, wrapping it in this delayed function, they'll use Python's decorator syntax this way. That's also totally fine. That's a very common pattern. I actually personally prefer this way. You're welcome to use whichever one you want. Then you'll see now increment here is this delayed function. So you can use the decorator syntax if you would like. That's totally fine. For here, for explicitness, we are delaying everything in line here. Now, because I've redefined my inc function, let me go up to the top and execute this cell again to make sure that my increment function is not delayed. Okay. So yeah, there is one section or one question here. What happens when you delay the function? What happens if you use the sum function directly rather than delaying it? So here I've delayed the sum function. What happens if I didn't do that? If I just called sum on results, where again, results is a list of delayed objects, we'll see that it still finishes and I still get the same result, and it still takes about the same amount of time, even though I use the built-in sum function. Let's compare visualizations real quick. So here is what it looks like if I use the delayed, this total here. I'm just copying that over and using delayed, and I visualize that result. I get something that looks like this. So here are my 8 different increments. I'm then adding them all together and getting my final result. So if I don't do that, I still get everything still works. I still get a Dask graph back, but it's much more complicated and gets a little crazy here. That's because the built-in sum functions implementation is to, when you have like an iterable of things, take the first 2 items, sum those together, then take that intermediate result, sum that with the next one, take that intermediate result, sum that with the next one, over and over. And that's what we're seeing here. So this graph structure is a lot more complicated and like more difficult to sort of comprehend, but we'll still execute and still get the same result. However, for my personal taste, I would prefer to delay this sum to get a nice, cleaner graph structure. Okay. Yeah, then that also reminds me, let me do this here real quick. So this will return a delayed object, and this will return a delayed object. And we can actually add them together and get back another delayed object. That's because delayed objects, you can add them together, multiply them together, and they will construct, as Darha said, they will construct the task graph for you lazily on the back end. So you don't actually have to work. You basically just write normal looking Python code, and Dask will handle constructing the graph for you. So here you can see here's us adding these 2 functions together. We get out a Dask graph. Okay. All right. This brings us to our next exercise. So previously we parallelized a for loop. Here we're going to do a similar thing, but with a twist. We're also going to introduce some control flow. So here we have a double function, which sleeps and returns 2 times the input, an is even function, which does not sleep. So this function is quite quick, and it returns whether or not the input is evenly divisible by 2. And then we have some data sitting here. So 1 through 10. So we now have these 2 functions in our data, and our sequential code will look similar to the previous example. We have some empty results list. We're looping over the data and sort of appending results to it. Although now we're going to have this extra step where, depending on what the item in the data is, if it's even, we're going to double it and include that in our results list. If it's not even, so if it's odd, we're going to include the incremented version. We're not going to double it. We're going to increment it and include that in our results. And then again, at the end, we'll sum all the results together. So we do that here, execute this code, and we'll see how long it takes and what our final result is at the end. Okay, so that took 10 seconds to execute, and our final answer was that we got out for this total sum was 90. So here, we will go ahead and parallelize this code using Dask Delayed. So I see there's a question. There's also a multiprocessing package in Python that parallelizes processes. Are there any advantages, disadvantages of Dask over that? So under the hood, and we'll talk about this a little bit later, under the hood, Dask does use the Python, or can use the Python multiprocessing module in the to execute tasks. So it will execute tasks in process pools. It will execute tasks in thread pools. The advantage of using Dask is the code you write is much more similar to the non-parallelized versions of code you're used to writing. So here, for instance, in the Dask Delayed notebook, we're writing code that looks very similar to the non-parallel version. And then to add parallelism, we just simply add this Dask decorator and then call compute at the end. It's still going to execute things in a process pool or a thread pool. We'll talk about how to specify which one later. But the syntax is very user-friendly. There's also, later on there's a lot of advantages of using Dask over the multiprocessing library. There's a lot of extra additional features and logic as well. There's a question, is order maintained in the output for parallelized for loops if the function runs for variable time depending on the inputs? Yes, so you're just setting up this graph structure and it will execute the graph. So all the dependencies, like run this before that, then after you're done with that, run this next thing, all of that will be maintained. All that order will still be there. So you will get the same result out at the end as if you were not running in parallel. You'll just get it faster. Again, there's a question about how does Dask handle parallelization, and then it mentions something about processes versus threads. We will discuss that later on in the tutorial. So yeah, you can use processes or threads or both, multi-threaded process, multiple threads in different processes using Dask, and you'll sort of want to tailor what parallelization resources you're using depending on your particular workflow. We'll talk about the pros and cons of using threads versus processes later. Okay, so I'm gonna share my screen again and go back to the exercise. Okay, so make sure I'm sharing, yeah. So let's go ahead and look at the solution here. Go ahead and copy this time result here. So this is a solution for parallelizing the synchronous code. You'll notice we've decorated a few, but not all of the functions. So we've delayed the double function, we've delayed the increment function, we've delayed the sum function, but we haven't delayed the is-even function. That's because it's being used in a conditional statement here. So what that means is, what we're saying here is if is even x, we actually need to know if x is even to evaluate. We need to cast it to a Boolean. We need to know if x is even or not to know which branch in the if else statement to go into. So that can't be lazily evaluated then. That means that we can't delay that computation. We actually have to have the concrete result here at this point. So delayed values cannot be used in control flow in that way. So you do need to be a little careful when incorporating control flow into your workflows. You need to be careful not to delay those results. So let's go ahead and run this. That actually just set up the computation. Notice I did not call compute anywhere here. So we'll call compute here and time that result. And that took 2 seconds. And we get the same result out of 90 as we did with the synchronous version. So before it took 10 seconds without Dask delayed. With Dask delayed, it took 2 seconds. So just to kind of reiterate that point again, let's see what would happen if I delayed is even here, if I had tried to, just like apply delayed to every function. I get an error. Truth of delayed objects is not supported. That's because this returns a delayed object, which we're trying to cast to a bool, which is not allowed. Okay, and we can then visualize this result. So here we see sometimes we're incrementing, sometimes we're doubling, depending on if the input is even or not. And then at the end, we're aggregating all those into a sum and returning the final result. So yeah, a few questions. So I guess we've already talked about this. What would happen if we had delayed as even? We would get an error. So casting things to a Boolean is one, like if else is one kind of control flow that can't be used for delayed. You can imagine like you can't also check if things are greater than certain values. Like you can't say, is this delayed value greater than 5? Because we don't know the value. Okay. That brings us to the last exercise here. We're going to parallelize a Pandas group by reduction. So this is a little more involved than the previous examples. So what we're going to do first is execute this cell here, which will download some data to your machine. If you're running in Binder, it won't download it to your local machine. It'll download it to the Jupyter Lab session running. And then we will go ahead and look at that data. So what this data is for flights out of New York City between 1990 and 2000. We link to the original data set here. We can see each year has its own CSV file. We can use Pandas to read in the CSV files. So here we'll use Pandas to just read in a single CSV file, flight data for 1990. And then we'll get the first 5 rows for the data frame. So we can see there's lots of different data here. Each row here is a different flight. So we can see year, month, what the arrival time was, what the carrier was, the flight number, things like that. A bunch of different information. We can see the data types here. So this is sort of a rich data set. There's object D types floating around. And we can get the origin for all these flights. So what airport did these flights depart from? And then we can call unique on them to get just the unique set of airports. So we have JFK, LaGuardia, and I believe EWR is actually Newark Airport. And then we can, so those are the origin. Those are like the airports that all these flights originated from. We can then group by the origin and get the average departure delay time for each airport. Again, this is all just for that 1 year for 1990. So we can see from Newark, the average delay departures is 9. I want to say the units on this are minutes. There's an X-ray tutorial later if you want to have units on your things. There's also JFK and LaGuardia. So that is the synchronous sort of example for a single CSV file. But now you want to analyze all the CSV files in this directory. You want to do this for each year. So what we can do is we can get all the file names here. We can glob this. It's the same thing as before. We're just now globbing and we have a star. So we're getting all the CSV files instead of just one. And then what we're doing here in the synchronous version is we are going to calculate the mean for these delayed times per origin or per airport. So we're going to have an empty list of sums and counts. This is how we'll perform this is sort of a standard way of doing averages over multiple data sets. You calculate the sum and the number of entries for each data set and then do an overall mean. So here we'll loop through each file name. We'll read in, we'll basically do what we did before. We'll read in an individual file, do a group by, get the departure sum, the departure delay count, and then we'll append those to the sums and counts lists. At the end, we'll then add up all the totals, add up all the counts, and then we'll take the ratio at the end to get the final overall mean. So we can execute this cell. It will take a little bit of time. It takes 4.84 seconds. And the final result we get out is this. So the exercise for this exercise is for us to parallelize this code snippet here. To do that, we'll need to know a little bit more information about Dask Delayed. In particular, we need to know that method and attribute access works on delayed objects automatically. So if you call a method of a delayed object, that will then return another delayed object. So for instance, here we're delaying NumPy's arange function that returns a delayed X object. We can then add 1 to it. We can then slice that array. We can then call a method, the sum method, and everything here will be lazily evaluated. That will set up a task graph for you automatically. You don't have to do anything special other than delay the original function. And then as well, while we have just been calling compute on single delayed objects, you can call, Dask has a compute function that you can call on multiple Dask objects. And what that will do is share intermediate results. So if there's a particular step in each of these computations that is shared in those task graphs, then it will only compute that once and share the results in both computations. So if you just called compute individually on each thing, it would compute that intermediate result twice. So this is a nice way to avoid that. And here's a nice result here. So we can compute y.min and y.max, and those will both share this x squared step. So when we compute both these things, it will only compute x squared once. So the goal here is to parallelize this code, which has been copied. Here we'll import compute from Dask. Here is the synchronous code that just been copied over again. So for convenience. And here in the exercise is where we will parallelize that. So stop for another minute and give some time to go through that exercise, and we'll answer questions in the meantime.
Okay, a bunch of people are getting a 9 on the JFK example you just showed.
All right. Getting a NAND.
In the meanwhile, do we need... Okay, go ahead.
I was going to say a question about the NANDs. For people getting NANDs, are you running on Binder or are you running locally? On JupyterLab locally, no NAND. So it's looking like NANDs are on Binder. Okay. Binder has limits on the amount of like space you can take up. So when you are launching Binder, we're actually only transferring over a smaller version of the data sets. So I'm suspecting what's happening is that we don't actually have the full data sets there, and we're getting NANDs in some of those fields. Okay, yeah, everyone who's having an issue is on Binder. That's my suspicion, is that that was an oversight on our part, that we don't have the full data set on Binder. Okay, I see. Thank you for posting that, Yuri.
Second one, do I need to think about the available cores on my system? How does it parallelize? I think we're going to get to this a little bit later in the talk. The answer is yes and no. A lot of times you can just, Dask will do the right thing, but there are cases where you do need to think about how you do chunking and things like that, depending on how many cores you have. So yes and no. Does Dask have an overhead where it may not be quicker for options for a large number of simple computations? I've noticed that sometimes I get better speed with a regular loop for certain calculations. Yes, Dask has an overhead. It's a fairly small overhead, but if your data fits in memory and is a serial computation, Dask is not going to speed anything up. If you have a more complicated algorithm where some of the things can be done in parallel, it will speed things up. Or if you have something that does not fit in memory, then it will give you ways to do those computations and spread it over multiple cores or multiple machines. Other situations where Dask does not do a good job of evaluating whether or not tasks or chains are independent, how is this happening under the hood? James, do you want to take that one?
Yeah, sure. So Dask schedulers will compute the order that they go through graphs, and it takes into account a lot of additional information. Generally, it's a pretty battle tested. The schedulers are pretty battle tested, so in general, it will do a good job. If you go to the Dask source code, you can see the exact order code where those decisions are made. They take into account things like, well, it depends on what scheduler you're using. We'll talk later. The distributed scheduler has a few more advanced decisions it makes with things like data locality when it's scheduling tasks. But yeah, in general, it does a good job. Okay, I'll go ahead and share my screen again. Okay. So let's go ahead and look at a solution here. So the solution, so going back up here, this is the synchronous version of the code. This looks very similar to the Dask version of the code, except for one difference. We are delaying the Pandas read CSV here. So we're not delaying other things like method calls. That's because those are automatically delayed for us. So here, this is whenever I delay Pandas read CSV, this will be a Dask delayed object. And then, so this will be lazily evaluated because it's a method call. Same here, And then at the end, we call compute on on all the sums and all the counts to share any intermediate computations, intermediate results. We can go ahead and execute this. And that took 2 seconds. So notice we are calling compute here. So we're not just setting up the task graph, we're also executing it. And that took 2 seconds. We get the same result. So yeah, sorry for people on Binder. It sounds like there's an issue with the data that's available in Binder. So there's going to probably be a NaN in your result here as well. But yeah, that should just be an artifact of the data available, not the actual code itself. So let's compare that to the synchronous result, which took almost 5 seconds. Okay, so I think at this point we are safe to move on to our first 10-minute break. I just, again, wanted to point out we have some documentation here, the delayed documentation, delayed screencast, and again, the delayed best practices document, which I highly recommend checking out. So we're now going to loop back to the beginning of this notebook where we instantiated that client and said, ignore it. We are now going to execute this cell and then also kind of ignore that. And we'll come back to this later in the tutorial. So at this point, we're going to take a 10-minute break. And we will then start with Darhas will then cover the O3_array notebook.
Okay, and while we're on the break, I guess we'll go ahead and finish answering the questions which are still here. We defined 4 workers, but it has 8 elements in the loop. How is that shared and computed? I guess we'll get to that when we talk about the scheduler. There is a scheduler that decides how to send all those tasks to the different cores and processes and stuff like that. So we'll get to that later.
By default, that will create a thread pool. Whenever you call compute, there'll be a thread pool or a process pool of a certain size. You can specify how many threads and how many processes you actually want to submit tasks to. By default, it'll find out how many cores you have on your machine and create that many threads or that many processes. So on a 4-core machine, there will be 4 threads or 4 processes. But you can also, that's just like the default behavior. You can totally say, I want 10 threads or I want 2 threads.
Why does it take 2 seconds? Why doesn't it take 2 seconds for workers 8 tasks? I don't remember the timing on that one.
Yeah, which example or which exercise?
Yeah, I don't think we have enough context for the for loop example. Okay, we've answered the NaN JFK one. That's because of Binder. Comparisons between Dask delayed and Job-Lit delayed.
I think they're quite similar. So I don't have a ton of experience with Job-Lit, but yeah, I think there is a very similar concept. There is, as maybe Mike will talk about later, I'm not sure what's in the Dask ML notebook exactly. There is Dask and Job-Lit interoperability as well. So they do play nicely with one another. So when calling compute, it will wrap the delayed operations together in a parallel way and give me the result. Yeah, so it won't, again, it will just set up the computation for you lazily. It won't actually compute the result, but yes, it will. If you have a delayed, like in the last example, a delayed read CSV, is to get a data frame, and then you call a method on it, it will construct that task graph for you. It will say, first call the Pandas read CSV function. And then after that, call the, I'm forgetting what method we called, but call the sum method after you've read the CSV. It'll set up that dependency for you. Could you just call X plus Y as well? Not exactly sure what example you're referring to, but yes, if X is a delayed object and Y is a delayed object, then that addition will happen seamlessly. Dask will take care of that for you. It will return a new delayed object, which is take X, take Y, add them together. That would be the task graph. Do we gain significant speedups by using Dask for parallelized work, or it just aids in using a larger than memory arrays? Both. It depends on your particular workflow. So it depends on your particular problem and the data sets involved. So yeah, certainly one of the selling points of Dask is that it scales to larger than memory arrays. If you wanted to load in a 1 terabyte array into NumPy, that you wouldn't want to do that. So you would want to use Dask. So it does help you scale to larger than memory data sets. It also is a general like dynamic task scheduler. So it also helps you parallelize works to get speed ups that way. It helps you, for instance, in our couple examples, we had for loops that weren't being parallelized. You can then use Dask to add parallelism to the same exact for loop. Where does the results.append y operation happen in the visualized tree? How does Dask Delayed know that it's associated with the delayed sum? So the results.append step is not like, that's just a normal list append there. So there is no Dask code happening there. The items we're putting into the list are Dask delayed objects, but we're still just building up a list of delayed values. So the thing that we actually visualize in the end is the summed result. So we then take that list of delayed values and then call sum on that. So yeah, the append portion does not involve any Dask code.
James, did you cover how to choose the number of workers in the first cell?
No, I did not. Yeah, so
I can take that real quick.
Sure.
So
that sounds great.
When you create that client, the local cluster, you can specify the number of workers when you create the client, or you can grab the cluster object out of it and scale depending on which client you're using there. So in this case, we're using the local. And so it will add more worker processes essentially when you scale or when you specify the number of workers. So if you already created the cluster, are going to do scale rather than creating a new one.
And again, that's for the distributed cluster, which we will talk about later on.
Mm-hmm.
More detail. Okay, so we are at 10 o'clock, which should be our end of our break. Darhas, I believe you're next with the array notebook.
All right.
Okay, hi guys. My name is Darhas Pothina. I work at QuantSight and have an original background in computational physics and doing a lot of hurricane simulations on supercomputers. And I really like Dask. It's a tool I've used a lot. Let me work out how to share my screen. Give me a second. Okay, let me make this a little bigger. In your folder, you should see if you look, you should see a notebook called 03_array. And that's the one I'd like you guys to open. How is my screen looking? Is that a good size for folks?
Could you increase just a tiny bit?
How's that?
Yeah, that looks good.
Okay, so we are now going to talk about Dask arrays. And the stuff we did so far with delayed is kind of like the low-level guts of how Dask works. And if you have a custom, let me make it slightly bigger. Oops. Okay, we'll see how that works. If you have a custom algorithm that you are trying to parallelize, using delayed functions is the way you go. But many times we use the higher, so Dask has its base delayed interface, and then it has several higher level interfaces. And typically, most people will be using the higher level interfaces and not the low level Dask delayed interface. but you can mix and match. So we're going to now talk about arrays. And a lot of you are probably familiar with NumPy arrays, which are basically a two-dimensional block or an n-dimensional block of numbers. It's just however many dimensions you have, 1, 2, 3, 4. It's just a block of numbers in memory. And Dask arrays provide an abstraction over those NumPy arrays to let you do bigger things than will fit in your own computer. And looking at the screen, what it does is it gives you a parallel larger than memory array system using blocked arrays. And one way to think of it, it is distributed NumPy. So that's the same API as NumPy, but on larger data sets. So you can do two. This gives you two advantages. One is you can run things in parallel. So if you have a large computation on a matrix or an n-dimensional array, you can use all the cores in your computer to run that. Or if you have a cluster, you can use all the cores in your cluster to run that. The other thing is it lets you work on data sets that are larger than memory. One of the problems I think a lot of us have had is we try and load a really large data set in, and then our Python kernel crashes because we run out of memory. What Dask arrays let us do is do operations on those larger than memory arrays by breaking it into lots of small pieces, doing the computations on these smaller pieces, and then putting them together. So effectively, if you have a really huge data set on disk that won't fit into memory, you kind of have a view over that data set and you walk through it piece by piece to do your computation. And it does this using blocked algorithms. And we'll talk a little bit about blocked algorithms, and we're going to build some ourselves to get a feel of how you would do this if you didn't have Dask. And then we're going to show you what Dask can do. So a lot of this tutorial is showing you how things work under the hood. But when you actually use Dask, you might not use some of these under the hood pieces. Now, here's some just links. There's some links in the notebook pointing you to examples and documentation and some other websites, so you can look at that. But initially, we're going to generate some random data. So just run the first cell. It'll take a couple of seconds, and it will generate a random data set, which takes a few seconds. And then, again, we'll talk about the scheduler and clients. This is the same as earlier. We're going to just set up a Dask cluster, a small one. And this is taking longer than I expected. Give me a second. So while we're waiting for that to run, I'm going to go down and talk about the blocked algorithm. So we take a large data set and we break it into small pieces. And an example is if we have 1 billion numbers and we want to calculate the sum of the billion numbers. Instead of calculating this, typically the way you do that with a NumPy array is you load the entire data set into memory. Okay, this is finished running. We load the entire data set into memory, and then we use a sum function on the NumPy array. But instead, we can break it into smaller chunks, like, maybe 1,000 chunks each of 100, like 1 million each. And then we calculate the sum of each chunk, and then we calculate the sum of the sums. So we calculate intermediate sums, and then we calculate the big sum. So we get the intended results, like the sum of 1 billion numbers. But we reduce memory usage by calculating smaller ones. So let's look at this. We are using the command we run earlier created an HDF5 file. Let me make this slightly smaller so we can see the whole command. Okay, so here we have the script we ran earlier created an HDF5 file, which is a binary file format that lets you hold data and lets you pull out data piece by piece. So it's a little bit nicer than using a CSV or something. And here we are opening this file in read mode, and we're pulling out a data set, which is the X value from this file. And this is actually, let me just show you. This is actually just a pointer to the data. It actually hasn't read this in. It's just said, this is a pointer to the data on disk, basically. And if you look, it's got 1 billion points. So let's work out how we would calculate this, the sum of this with a blocked algorithm. So I'm going to walk through this. What we're going to do is we're making a list called sums that is just holding our intermediate sums. We're going to just do a loop from 1 to a million, 1 to a billion, going 100,000 at a time. And we're going to pull out one piece of the data, and basically we take that D set, which is basically the X data from the HDF5 file, and we are going to, in each iteration of the loop, we're pulling out one chunk. We're going from 0 to a million, 1 million to 2 million, 2 million to 3 million. So we're taking out a series of chunks, each of which is a million in size. And then we are calculating the sum of each chunk, and we're appending the sum of each chunk in this list. And actually, let me remember how to do this. Let me split cell here. So if I run this, this is looping through all the files. And if we look at sums, this has the intermediate sums of each chunk. And now if we calculate the total of the sums, we get the total, which this is a randomly generated number, so your value might be slightly different from mine. Now, as a quick exercise, let's see if you can take this information and do the same thing for a mean. And so you've got the instructions. We're going to compute the sum of each block, compute the length of each block, then compute the sum of the 1,000 sums and the sum of the 1,000 lengths, and then divide one by the other. So I'll give a couple of seconds to see if you guys can, you should be able to copy and paste the code from up here, and then do a mean instead of the summation. So I'll just give you guys about a minute to try that, and then I'll walk through it. And let me look at the questions. Oh yeah, the folks in Binder might not get the same answer because I think you're using a smaller data set. It looks like you're using a data set that's more like about half or less than the size. So the answer you get is different. Okay, Binder has 5 million, so it has a smaller data set. Let's see if there are any questions. Okay, let me walk through this now. So similar to above, we're just adding an extra thing. We're calculating the lengths. And then in here, we're getting, as earlier, we get the sum of a chunk. And then we append the length of each chunk. And now if we total the sums and total the lengths, we can get the mean. And this takes a little while because it's walking through everything. Now, this is what you would do if you were doing it manually. If someone gave you a larger than a memory data set and you had to work out how to calculate these algorithms yourselves with a larger than memory data set. Sum and mean are very simple, and you can kind of reason through them. Other algorithms can get more complicated. And what Dask Array does is it implements these algorithms for you. It is basically a library that mimics the NumPy API and does these kind of tricks to perform the same NumPy algorithms on larger data sets that don't fit into memory. It does not implement every single piece of the NumPy API because the NumPy API is quite vast, but it covers a majority of the most used pieces. Now let's go back and repeat this using Dask Array. And so we're going to import Dask Array as DA, and let's look at this command. We're going to use a new command, Dask Array from array. Okay, and what this does is it can take any object that is array-like. Like, for example, here dset is a pointer to a file that can give you back a NumPy array. And so what from array can do is take this and create a Dask array. And we have an extra piece. We have to tell Dask how we want to break up the array, because Dask is going to break up the array into pieces, which we're calling chunks. And we have to tell Dask how to break it up. In this case, we have a one-dimensional array, so there's only one dimension to the chunk. And so when we do this, we're creating an X. And if you look at this, each value, each chunk, so this is a 4 gigabyte array, and each chunk is about 4 megabytes. The shape of the full array is 1 billion elements, and the shape of each chunk is 100,000 elements. And so you have 10,000 chunks. So again, here we have not, this is going back to delayed. At this point, we have not read anything directly. We have not read in any data. We have not done any computations. We have just made a pointer to all the data in some sense. And now, we have a similar API and interface to what you would have in NumPy, but under the hood, we have this distributed Dask array. And so we can do something like, let me see if it's further down. Yes, so if we do here, we have results and result.sum, and result.sum still has not done anything. It's just a 4 kilobyte thing, because again, remember, Dask is lazy. So things like sum and other NumPy functions don't actually compute anything. They build up that task graph we were talking about earlier. If we actually calculate the result by using a compute, now we will see the answer. So now when we've done the result.compute, it's actually taken it's walked through the data set on file, it's loaded each chunk, and then it's computed the sum on each chunk, and then it's gathered all the chunks together, and it has done that. Actually, let me see if I can do this. I'm pretty sure this will work, but now this is taking a little longer than I expected. So if you do result.visualize, you should see, I'm not sure why it didn't show up. Okay, it's very tiny. I see it's I don't know if you can see this or not. Yeah, it's very faint, but the graph is so big that it made it into a very tiny image. I'm not sure if I can pop that out. Yeah, I'm not going to worry about this. If you see very faintly, because it has 1,000 elements, the image is stretched across the screen, and I think because I'm zoomed in, it looks a little weird. So anyway, but the result of visualize does show you the actual result. Okay, quick example. How would you calculate the mean? Okay, let's see. Someone said that if I double click it, it should show up. No. Maybe. Oh, there it is. Yeah. So there it is. There's the big. So if you look at this, right at the bottom, we have all these arrays and the chunks, and then it's calculating the sum. If you look in the middle, somewhere here, there should be a read, but I think I have to zoom in more for that. And then we go up, we calculate all the sums of the individual chunks, and then it's actually calculating partial sums for groups of chunks, and then it's calculating the sums of those and calculating the sums of those, and then you finally end up with the final answer. So that is the complicated task graph. Now, when we did our examples with the delayed for the for loops, we kind of went through some individual, it was a very simple task graph, and it made sense to walk through it very straightforwardly. When you have a lot of tasks, like 1,000 or more tasks, that we may want to go through the task graph differently. And if you look on the right of my screen, there's an image where I think red is when a task is being executed and blue is when it completes. And if you look at it, it's not going in a particular order. It's kind of going in a slightly interesting manner. And what it's doing is it's trying to use multiple cores in parallel, and it's trying to chain operations on single blocks before it moves to the next one. Dask array, it takes your array operations and builds it into this task graph or a directed acyclic graph of interrelated tasks. And these tasks have dependencies in between them. And it's working out what those dependencies are, building the graph, and then when you run compute, Dask then executes the graph with multiple threads. And we'll talk more about this a little bit later. Someone asked about OpenMP or MPI. I would say a big difference between OpenMP and MPI is with those, you're explicitly defining what the task graph is. You're telling MPI or OpenMPI how to compute things. Dask is kind of doing that for you. Okay, so did anyone? Let's look at for an example for the mean. It should be x dot mean. If you do x dot mean, oh, that didn't actually do anything. It just gave you a delayed object. So if you do x.mean.compute, now it'll actually compute the mean. And so any of the array objects, NumPy APIs you can use with a NumPy array, you should be able to do something similar with the Dask array. If you look at X and hit tab, you have the same argmax, argmin. You've got a couple of extra things like chunks, which NumPy doesn't have, and compute, but then CumSum, dot, all these different things are available. Another point, which someone's mentioned, that Dask seems to take longer. If your NumPy array fits in memory, and you're doing a single computation like that is in serial, you won't see much performance benefit over using NumPy, because NumPy is already very optimized and very well built. Dask is going to be more useful when you're building computations that can be parallelized or computations that don't fit in memory. Now, going down here, let's look at another example. we're going to create a 20 by 20,000 array of random, normally distributed random values. And this is two-dimensional now. So when we're doing two-dimensional and we want to make it a Dask array, we have to kind of say how you want to chunk it in each dimension. And for simplicity here, we're taking 1,000 in the X direction and 1,000 in the Y direction. But depending on your matrix, your block size, we can vary these chunks to be more efficient in the way we read things. And then we're going to try and take the mean along one of the axes and take every 100th element of that. So if we do that, if we look at the size of this data set is 3.2 gigabytes. So it's a pretty large data set. And now let's time the compute. It should take a couple of seconds. Should be using 4 processors on my machine right now. Took about 18 seconds. Okay, so this is just the data. Now, I'm going to walk through some performance comparisons right now. We're not actually going to run these, but this following section was built on a pretty strong laptop. And you need about 4 GB of main memory to be able to do this. So if you use straight NumPy and you do this computation, it takes about 19 seconds. Just using NumPy, random, normal, and just doing the mean. If you use Dask array, it should take, so the first one needs gigabytes of memory. You need to load the entire data set into memory, and it's probably going to be at least 4 gig or more. If you use Dask array, instead of using 4 gig of memory, you're only going to use megabytes of memory. And it should parallelize in a way so that the computation happens much faster because it can use all the cores in your machine. So it should, this particular benchmark dropped down to 4 seconds and a order of magnitude lower memory use, maximum memory usage. So also notice that the Dask array computation ran in 4 seconds, but it used 29.4 seconds of user time. And this is because it was using all 4 cores. And so that count is because of the transparent parallel computation through the chunk size. Okay, so let's see if you guys can answer these questions in the chat, and we'll see if anyone comes up with answers. What would happen if we increase the chunk size to 20,000 by 20,000? How much would the computation be faster, slower? How much memory do you think we would use in terms of peak memory? Hoping some folks would be brave enough to answer in the chat on these questions. Well, no, I'm not. So the question is, if we specify the chunk as 20,000 by 20,000, the same size as the array, what would happen? Okay. Yes, so Orhan kind of has it correct. If you specify the chunk really large, at the size of the array, essentially there will be only one chunk and it will be calling NumPy. So the computation would be the exact same computation as NumPy and the exact same memory usage as NumPy, plus a little bit extra because of the overhead of starting Dask. So it would be a bit slower than NumPy, is the case. Now, what happens if we make the Dask chunks 25 by 25? Yes, so as Grace said, if you make the chunk size the size of the array, it's the exact same thing as just using NumPy directly and loading the whole thing into memory. Okay, what about if we make the Dask chunks really small, 25 by 25? So basically, if you make the chunk size too small, your overhead is going to kill you. You will use a lot less memory, but you'll have a much higher CPU overhead because Dask has a very small overhead per task, but there is a certain set. So essentially what Dask is doing is splitting the computation into lots of smaller function calls, and every function call has a certain fixed overhead. So that fixed overhead will start piling up. And so choosing the chunk size is important, and it doesn't have to be the same in each dimension. There is actually another project called Xarray that I think there's another tutorial for that uses Dask Array under the hood. And if you had gridded data like NetCDF data or something else like that, Xarray is actually a higher level interface onto some of it, but you still have the same chunking issues. How do you find the Goldilocks of chunk size? The chunk size issue is something very difficult to have a single one size fits all, because it sort of is determined by the kind of algorithms you're trying to write and also the kind of compute power you have available and the kind of cluster you have. So it is sort of trial and error in some sense. There are some rules of thumbs you can use, but yeah, to some extent it's trial and error. Okay, let's move on. We have another exercise, which is instead of using, random data is always nice, but it's random, and it's less intuitive. So we're going to create a new data set, which is based on some temperature data, average temperature data of the Earth. And if we run this, it'll pull some data for that. While that's running, let me have a quick look at the questions, if there's anything. Okay, the questions. Trying to see Dask Array. Show the output of an array in the notebook. What do you mean? Like any array? Well, I'm waiting for this thing to run right now, so I'm going to have to wait a second. Okay, so we created the weather data set, and it took about 71 seconds. Now here I'm just going to, so if we look at this weather array, let me see, it's in, oh, did I get that wrong? Oh, wait, no. Okay, so if we look at this, it is a collection of files that are each about 500 MB. Let me see, du minus h. The total. The total size is about 17 gig. So this is a pretty big data set. And one of the things which is nice about Dask Array, and also if using HDF5 and things, is we should be able to open multiple files into a single data set. And so here we are using a glob to get all the HDF5 files, and we're making a list of dsets. So if we look at dsets, it's basically pointers to each file, and each file has an array which is this size. And so if we looked at the dset of 0 over here, this is basically one data set of this size. Now, the way we're using H5Py to reach this HDF5 file in, and we can use regular NumPy style or Python style slicing to pull out a small piece of it. So this is just taking the first data set, which is a two-dimensional data set, and pulling out the first 5x5 elements. Now let's just plot a small data set. So we're just taking the first raster, like the 2x2 thing, and subsampling it by every fourth element. So this is just a way to make it a little smaller, because otherwise this plot might take a long time to load. And this will take a couple of seconds. And what we're going to do is we're going to convert all these regular NumPy arrays or H5 arrays into Dask arrays. And okay, so here's a plot of the temperature for one of those data sets for the entire US. I think that is Australia. There is North America, South America. It's cold near the North Pole anyway, and the South Pole. So looks reasonable to me. Now let's take all these Dask arrays, and we're going to all these NumPy arrays, and we're going to read them into Dask arrays, looping through each data set. So remember, dsets, if you do len, dsets is a list that has 31 data sets in it. And for each data set, we're using da.from array with a chunk size of 500 by 500 and converting it into a list of Dask arrays. And so if you look at this, each of these is a two-dimensional array. And now we want to put them all together into one larger data set. And so we're going to use a command called da.stack. And we want the final version of the final version of the data to be actually a three-dimensional array. So we want it to look like 31 by 5760 by 1120. So the way we're going to do that is we're going to use the stack arrays command. And if you look at da.stack, it kind of tells you this is kind of thing. It lets you stack a bunch of Dask arrays along a particular direction. So in this case, I'm going to stack the arrays. I'm giving the list of arrays I want to stack, and I'm going to stack it along the 0th dimension. And if we look at this, this will now build our three-dimensional array, which is 31 by 11, 15, 20 by 5760. And it's chunked into blocks. And each block is one element high, 500 wide, and 500 long, I guess. And so it's little blocks that form this big thing. Now, let's see if anyone can get this. How do you think you can complete this code and calculate the mean of this array along the time, which is the 0th dimension? So the 31 are 31 date times, basically. So why don't we spend a couple of minutes trying this? Just think how you would do this in NumPy if you wanted to get a mean along one axis, and see if you can work out how to do the same thing in Dask. Oh, let's try. Someone had a suggestion in the chat. Let me just see. Let's put that suggestion in and see if it works. Oops, that didn't work. 1 second. Okay, let's try that. It's chugging along. And I think this is going to error. And we will see why it errors in a second. Okay, I'm actually going to kill this because it's taking a little extra time. Okay, let me just kill that just since it's taking a little bit longer. But essentially, oh wait, I was on the wrong place. Sorry. So one of the things which came up, so this was actually working. I killed it because it was taking a long time. This was the correct answer. Some people mentioned that why don't we use compute? And typically you would use compute, but there are some places where, like, for example, if you do a len on this, len is required to have a value inside. So it does a compute automatically. And so this result, the IM show, when you put it in a plot, it implicitly does the compute for you because it needs the data to do the plot. If that kind of makes sense. So you could either do this or you could do compute. Both will do the same thing. And you should get a plot from above. So yeah, so let's try and see if you can do this. I'll give it a little bit of an extra time here. Let's see if you can calculate the difference between the first day and the mean.
I guess we can look at questions. And yeah, like Darha said, matplotlib under the hood will actually convert the Dask array to a NumPy array. It'll do that computation under the hood. That's why you can pass a Dask array directly to matplotlib, and it will do the computation and plot it for you. It's nice that you get the plot. You don't have to call compute explicitly, but you do need to know that matplotlib will do that computation for you. So just something to be aware of. Looking at the questions, at some point, could you elaborate on the limits of Dask array? Where do we start getting too big of a data set for Dask to handle? So too big of a data set for Dask to handle. So one thing, there are a couple things to keep in mind there, a couple limitations. And they're not really, they apply to Dask array, but they're specific to other collections like Dask DataFrame as well. Is you want to make sure that your data set can fit in your distributed cluster memory. So, if you have, Dask will spill to disk whenever memory starts to become an issue. So if it starts to run out of memory, it'll write intermediate results to disk and then to save RAM, and then it'll just pull those intermediate results out as necessary. Although that, as you can imagine, writing and pulling from disk slows things down. It's not as performant. So in general, I would try and have your data set fit into the entire distributed memory, although it will work if it's larger. The other thing to think about is the number of tasks in your task graph. So there is some overhead associated with processing each task in, like, say, a Dask array. So when your chunk size is really, really small, that's good because from a memory perspective, because you'll only load in a few chunks at a time. So if your chunks are really small, then you'll be well below your memory limits on your cluster, and that's great. The downside is you'll have lots and lots of tasks that you're processing, and there is some overhead with each task. So that will eventually become a performance issue if you have like millions and millions of tasks in your graph. It'll still process, it'll just take a really long time to actually process all those tasks.
Okay, let me get back to this. Now, I'm going to walk through this. Let's look at this result. And so here, it's actually fairly straightforward. We want to plot the difference between the first day from the mean. We know how to get the data for the first day. We know how to get the data for the mean. And now let's actually split this here and let's see what this looks like. I always forget the shortcut for split. Okay, so if we look at this, this actually didn't do anything. It's just another delayed object. But when we throw it into the figure, it should run all the computations. And so you're using the same kind of API the way you would use it in NumPy. Now, this is a key fact that's going to be important for both Dask Array and Dask DataFrame is, okay, let me reiterate this thing, why we don't need to call compute. There are certain functions and certain libraries that know how Dask works. And if you pass them a Dask Array or Dask DataFrame and they need the result, they will do the compute automatically for you. But there are other functions which, but those libraries have to be Dask aware. So if you just take a random library and give it a delayed object, then it will break if it's expecting an actual realized object. Okay, so getting back to this. When we do something like a result.compute, so right now result is a delayed object. Oh wait, no, result got computed. Never mind, let me kill that. Oh no, it's fine. Okay, so result is this delayed object. It's actually very tiny. It's only a couple of kilobytes. It doesn't take up much memory. If I do a result.compute, it does all the chunked calculations and then brings all of that data back into the main memory of your computer. And so if your computer does not have enough memory to hold everything in the to hold everything in memory, it will crash your kernel. It won't actually work. So you have to be very careful when you do a dot compute or you do something that brings everything back into memory, that either your data is small enough that it fits in memory by doing a filter or something else, or here is a set of instructions on how you would, instead of pulling it to memory, we are going to write it to disk. So we're going to use da.toHDF5 or da.store. You can use one of these two functions. And what this will do is it will process the data in parallel and save each chunk to disk as it's processing. So you never pull the whole thing into memory. I'm not sure. Maybe we should just skip this exercise in the interest of time. And so something else to consider if you are doing really large data sets, there's a project called ZAR, which is a really good way to write really large gridded data sets. So, James, what do you think? Should we stop the array part here and move to DataFrame? I'm not sure if we should do this last exercise.
Yeah. How many more exercises are there?
I think it's just this last, the Leonard Jones potential one.
Okay. I think we may be okay then. So I think right now we have scheduled another 10-minute break.
Okay.
Maybe do we want to go over this limitation section real quick?
Yes,
and then
I'm not going to go through the last exercise. I'm just going to go through some implementation, some limitations. Dask Array does not implement the entire NumPy database. There are bits and pieces that will not work. It does not implement all of the numpy.linalg. One of the reasons for this is there are some really excellent low-level libraries like Glass and LAPACK that actually will do a better job than Dask does for those kind of computations. So you shouldn't really be using Dask to mimic those. It also does not support operations where the resulting shape depends on the values of the array, because Dask does not know, like if you what we did earlier with the if condition on the delayed object, where we needed to know the value to evaluate the if condition. Same way, if you have some algorithm that requires the resulting shape be dependent on the values of the array, Dask can't do anything with that because we don't know what the data is until we do the compute. There are certain things which are inherently difficult to do in parallel, like sort. And this is not a problem with Dask. This is just an overall issue in the way how distributed systems work. There are some operations which are just inherently difficult, and we usually have a parallel-friendly alternative, but there's some pieces which are not true. The last bit is important. Dask development is basically done by volunteers and staff at different organizations, and the development is based by need. So, my company needs certain things in Dask, and we fund the development of those features. So there are some functions that are not implemented just because no one's done it yet. And if you have a certain function that you really like and want to use, contributing that would be an amazing thing to do. So getting involved is definitely a good thing. So I'm going to run client.shutdown, and it should just close my cluster. A couple of things. Folks who are working on Binder, you might see warnings because the CPU time and the compute power that folks give you on Binder are a lot smaller. The other thing is, if you're on a local machine, if you just use client instead of saying n workers equals 4, it will just use all the cores on the computer. So if you want to use all the cores on the computer, you can just say client. Okay, I think we're going to take a 10-minute break now before we start the Dask DataFrame. I guess we'll start at in 10 minutes from now. That's roughly 11 a.m. CST. In the meantime, I'm going to stay on and look through the questions. I might skip some of the questions from the earlier exercises because I don't think I can find the context. So I'll try and answer the ones which I can understand the context from. Okay, so Cooksian ran out of memory using IMShow. There's actually another project called Data Shader in the HoloViews tool stack, and that's actually a better way to visualize very large data sets, but that's out of the scope of this. But the Data Shader and HoloViews actually use Dask under the hood, so you can visualize very large data sets without running out of memory. Okay, what can I say about using all 4 workers? So at the beginning of this notebook, we did this, let me find it. At the beginning of the notebook, we set up a client like this. If we change this to this, then it would set up a client with all the processors on your computer. So if you had 8 cores or 2 cores or 4 cores, it would set it up with the appropriate number, like using some defaults. And later, James will be going through the schedulers in more detail. And so he'll give more options on how those different pieces work. Okay, if you have particular questions that you are interested in, please vote them up. It makes it a little easier for us to walk through and see which questions we need to answer. Why is the sum from the Dask array implementation different from the chunked implementation up top? I would say, and I haven't looked at it exactly, but Dask does a lot of tricks to optimize task graphs. So when we built things manually, we were kind of just doing a very simple parallel algorithm. But actually, Dask builds a task graph and then does an optimization stream to rearrange some of the tasks to be more efficient in the way it computes and runs on different cores and stuff. So probably that's the reason why it's different. Yeah, and that goes back to Maggie's question as well. In the visualization I showed for the sum, it was actually doing some groups summing and then summing the groups and then summing the groups. And that was probably an optimization to make the compute more efficient. So the HoloViz tool suite is a good tool suite for visual data shader and HoloViews and bokeh and GeoViews. These are all a set of visualization tools that work with Dask under the hood that let you, or HVplot is the other one. They're all part of the same suite, and they use Dask under the hood, and so you can do very big data sets in your browser very easily. Let's see. So is there a way to port arbitrary NumPy-based function into Dask by just passing a Dask array into it? I think you'd have to use the Dask equivalents of those NumPy functions. There is some new work. There's some ongoing work with the NumPy group where you use NumPy more as an API, and then under the hood you can use different backends like Dask or GPU or stuff like that. But I think that is not fully mature yet. It's more like a in development feature. Could Dask handle communication between chunks? I'm not sure exactly what you mean by that, because the chunks are just pieces of data, but Dask does handle moving data around from different machines and processors as needed to finish the computation, if that's what you mean. Can Dask be used in a multi-node setup? Yes, we'll get to that in the distributed section. Okay, any other questions? Let's see. How does Dask compare with Number? You can kind of use, they're kind of doing two different things, and you can actually use them together, and actually a lot of projects use them together. Number will speed up a particular piece of code by doing just-in-time compilation of that code. Dask helps you distribute computation across cores or across nodes. Okay, can you convert a CSV file to HDF5 files? That's probably not the best idea, but there's another format called Parquet, which is a binary format, and it's very straightforward to convert CSV files to Parquet files. And Dask, actually, most tools work a lot better with Parquet files than CSV files. There's a lot of good advantages to using Parquet files. So I've seen several questions on, can I do XYZ with Dask? And I will mention this. Dask is kind of the fundamental building blocks for doing a lot of parallel computations. You have the Dask delayed interface, the Dask bag interface, the Dask array interface, and the Dask DataFrame interface. And we're going to go over 3 of those today. There are also other libraries that are built on top of Dask for different things. Like Xarray is a really good library if you're doing very big raster or n-dimensional data type computations, especially in geosciences and other things. There's Dask ML, which implements a large number of, it uses the same Scikit-Learn API, but implements a fair number of those algorithms in a parallel structure. So there is another suite of tools that sit on top of Dask and use Dask underneath the hood to do specific things. So the examples.dask.org website has some links to those. You can also ask in the channel and we can point you to specific ones. Okay, what does the D set F/X? So this is a particular thing. So walking through this, HDF5 is a binary data set that looks like a directory. So it uses a single binary file, and in that binary file, you will have a, let me actually do this. So if we run this, if you look at F is a H5 file pointer. It just points to a file, and I think it's F dot. So it looks like a directory structure. It mimics a directory structure. So inside F, there is a folder called X that contains the array called X. So dset F of X gives you a pointer. So this essentially gives you a pointer to the X data set inside this file random.hdf5, if that makes sense. And then you can load pieces of that data. So it's a specific way of loading HDF5 data. So does Dask automatically compute chunk size? It can, but you also sometimes need to pick it yourself depending on the type of computation you ran. The high-level point I'll make with the Dask array and Dask DataFrame is it does a lot of stuff very well out of the box. And you can go very far without having to remember that you're on a parallel distributed system. But fundamentally, parallel algorithms and distributed algorithms are different from serial algorithms. So at some point, you will need to understand some of the complexities of working in a parallel system. And so automatic chunking, great, you can use it, but in some cases, you may have to pick your own chunking to optimize performance. Okay, why do we have to assign x.mean to result? Wouldn't it work inline? Yes, it would work perfectly well inline. We just did it to make the tutorial clearer for folks so it wouldn't get confused. So if you're on Binder, you may want to change your data set to whether small, and that will maybe not hit some of the memory issues that folks are hitting on Binder. Dask array returned a value that's rounded differently than the non-Dask version. I think that's something that can be controlled. I'm not exactly sure on how you do that, but I'm pretty sure that's can be controlled. That also might be something which is just you need to check that. That might just be how it's printing, but we would need to check that. Yeah, so James said it's just the way the HTML is being printed in Jupyter, but the actual numbers are the same. James, do you want to take this one about whether we keep any of the, we don't compute the results from x.mean, but there are ways to persist some things in memory, and there's actually a persist Well, we'll probably look at that in another place, but there are ways to keep some things in memory if you expect to use them again later. But yeah, okay, Mike is going to cover persist in one of the notebooks later. Okay, when do I need ZAR? Okay, so HDF. Okay, some history. HDF5. So if you're using very, very large data sets, you should not be using text files. You should not be using ASCII, CSV, or any of that kind of stuff. That's very inefficient. You don't have any information about data sets. Data types. You can't read bits and pieces of the files. The HDF5 is a file format that was developed quite a while back, and it fixes some of those things. So it's very easy to have really large binary data sets and pick little pieces of them for n-dimensional data. ZAR is a newer project which takes a similar model to the HDF5 format, but makes it more cloud friendly because with HDF5, if you put HDF5 files on the cloud, you can only read all or nothing. You can't read a piece of it the way HDF5 works. ZAR keeps the metadata in a separate file and chunks the binary pieces in little pieces. So if you put the data in some kind of remote storage, like on S3 or on a remote file system or something, then you can transparently, if you ask for a small piece of the data with Dask or with something, it will read the metadata and work out which pieces it needs to download and only download those. So that's one of the reasons why I use ZAR. It's a really great project. I highly recommend folks who are looking at very large n-dimensional data look at ZAR as a way to handle their files or their data. So, okay, I think that's about end of the break time. So let's switch to the next section.
One quick question. Someone's asking how to find the solutions to the exercises in the notebook. There are ellipses. Those cells are essentially hidden. So if you click on those will expand and you can get the answers.
Yeah, I'll see if I can find one.
But no cheating.
Yeah, somewhere you should see some ellipses, like 3 dots, like the 3 dots here. If you click on those, it expands to the solution. So anyway. Okay, so now I'm going to open the DataFrame notebook, and Dask data frames are the equivalent distributed version of Pandas data frames. Similarly to how we built NumPy Dask arrays on top of NumPy arrays. So in chapter 1, we did a parallel data frame computation over a directory of CSV files using Dask Delayed. That is a really annoying way of doing things, and what I'm going to show you is a much simpler way. And the approach, again, similarly to NumPy, the times when you want to use Dask data frame is when the computation you're doing could be made parallel, or if your data is bigger than memory. If under the hood, Dask data frames are going to be using Pandas. So if you have a tabular data set that fits in memory, just use Pandas. Dask becomes useful when you have really large data sets that don't fit in your memory's RAM. The demo data set we're using is small, so it's not actually going to run out of memory. So we're just using it as an example to show how to use Dask data frame. But this technique will work on extremely large data sets. One of the projects I do at work, we actually have data sets that are in the terabyte, 20 terabyte zone, and we use Dask DataFrame to do processing on them, do analytics on these really large data sets. So you can, for a lot of people, Dask DataFrame is going to be the main API they use when they use Dask. Again, it mimics a large subset of the Pandas DataFrame API, but not everything. And this is for two reasons. One thing is the Pandas API developed over time, and it is massive, and it is really not possible to have every single part of the Pandas API in another project. But a large portion of the main parts of the Pandas API are implemented in Dask. And there are some things that are inherently hard to do in parallelism. And those things, there are sometimes workarounds, or sometimes there's just not a way to do those. Again, some documentation links. And the main takeaways is, if you know Pandas, you pretty much know Dask DataFrame. Pandas is a in-memory serial data frame. Dask is a parallel distributed version of the same thing. The second takeaway is the way you partition the database can be very important for efficient execution. Okay. Thought there was a diagram here, but anyway, let's create the data. And it's downloading some flight data, and then I'm going to get a client set up. So this is going to take a couple of seconds to download. Wait, there should be a diagram which seems to be missing. Let me see if I can go to maybe it's later done. So this is kind of the diagram I wanted to show you guys. Similarly to how we had blocks in the in NumPy array, we split the array into uniform blocks in X and Y. With Pandas data frames, we don't. It's a table, so we don't exactly have multiple dimensions. The Pandas data frame is a two-dimensional table, kind of like an Excel spreadsheet. And so we don't actually split it in multiple dimensions. We only split it in one dimension. And that dimension is the data frame index. And here's an example of a Dask data frame made up of multiple small Pandas data frames, each containing data from one particular month. And you also see the sizes of these partitions are not uniform. So that's just a quick aside. I'm going to go back here. Hopefully this is finished running. Okay, this is finished running. And now I am going to, this also does some data prep. One of the things which I'm going to show is file name is a glob, okay? It is a pattern to match something. So we're going to match accounts star.csv. In Pandas, you would read something as import Pandas as PD, and then you'd say df equals read PD dot read CSV. Probably something like this. This is how you'd read a single file inside Pandas data frame. Dask data frame, we usually import it with a import Dask as DD. And instead of giving it a single file name, let me split this here again. Instead of reading a single file name, I gave it a glob or a pattern of file names. I gave it this pattern. And now if you look at df, df is now a delayed structure like earlier. It actually doesn't have anything. It's just got this delayed structure. It also, if I do an ls of this, wonder if I can do this. 1 second. Let's just see how many we have here. We have basically 3 files, 0, 1, and 2. And if you look at this, Dask is going to call read CSV 3 times to read those 3 files in. And that's just what this little piece means. Now, if I do a df.head, it's going to take a couple of seconds, and it's going to read the first 4 or 5 elements of this combined data set. Now, if I look at len, it's actually going to do a couple of things. It took a couple of seconds, and it found the length of the data frame is 300,000 rows. So what happened? Dask looked and found that there were the 3 matching files, the ones we saw up here. It found these 3 files. It calculated the length of each chunk. It loaded each file into memory and calculated the length, and then it added the subtotals to combine that into a grand data set, in a full data set, a full subtotal. So now let's try this with some real data. We have another folder, which is called, this data NC flights star.csv. And, this is just, this is the same information you would give pandas, with the only difference being, instead of giving it a single file, we're giving it a set of files. And this also could be a list. You can give it a glob, or you can generate a list of files, and you can give it a list of files. So Dask just did enough work to work out how many files are there. Like, there's 10 read CSVs, and it did a little bit of investigation to work out what the data types were. I just looked at the first file, and it picked some data types. Because it's a CSV, you don't have actually any information on what the data types are. Even in Pandas, when you do read CSV in Pandas, it looks at the data and tries to guess what the data types are. And so if we look at df.head, this worked great. You got the date, you got the day of week, you got all these other, different fields. Everything worked great. Unfortunately, this broke. df.tail. And if you go down this big error, you go down, it's quite a long way. It gives you this error that there are mismatched data types. And it gave you these 2. One is that there's this, it was expecting an integer and it found a float. It was expecting a float and it found a object, which is a string. And explaining this, Pandas read CSV reads the entire data set into memory and then works out what the data types should be. The Dask DataFrame version on it doesn't do that, because if you read the entire data set into memory to work out what the inferences were, then you're defeating the point of doing things in parallel and using Dask to reduce memory usage. So it looks at the beginning of the file, or if it's a huge file, or if it's a set of files, it looks at a couple of the files and it tries to guess what the data types are. In this particular example, the first 5 or 6 rows have no value for CRS elapsed time. Like, if we go back up here and we look at CRS elapsed time, I guess it's one of the, okay, I'm not going to go there. It's one of these nans. There's no values at the beginning of the data set. Okay. But at the, so it assumed it was, a float because there was no value. Later on in the last data set, there were strings in that column. And so it's an object. So Dask gave an error saying, hey, I thought it was a float, but it actually turned out to be a string when I tried to reach the last one. So when something like this happens, you have a couple of options. One is you explicitly say what the D types are. You use the D type command and you explicitly say, this is a string. This is a integer, whatever. This is the recommended solution. If you know what your data type is, hard coded in so Dask doesn't have to infer it. If not, you can increase the sample size so it looks at more of the data before doing the inference. Or the other thing is, till recently, integers, so NumPy and Dask use np.float as a missing value, and integers did not have a float, like a missing value type. So if you had a data set that was integers and had a missing value, it would get converted to a float. But when you look at the first few rows of the data, if there are no missing values, it will make the type an integer. And then when you read the last data set, there's a missing value in there, so it tries to read it as a float. And when it tries to do the whole thing together, it breaks. And so you can use an assume missing command to, so you can either use an assume missing command, or you can basically just make it a float. So we're going to use the first option, and we're going to specify the D types of the columns that are breaking. So we're going to say tail number is a string, CRSE elapsed time is a float, and canceled is a Boolean. And now if we do that, Dask knows what the data type should be, and so tail works. One of the takeaways of this message is CSVs are a really sucky format for data. Please stop using them and use something else like Parquet or HDF5 or anything else like that. A lot of problems you'll have with very large data sets will come from the fact that CSV files are messy and annoying. Okay, so let's look at an example of how we would do similarly for the example we did with the array computation. If we had a set of CSV files, and if we tried to read them all into memory at the same time, and they would be too big to fit in memory, how would we do that without while minimizing memory? And okay, someone commented that CSVs are readable. CSVs are readable when you have small CSVs, but when you have like terabytes of data, CSVs just become impossible to use. So you can do a df.head and read it that way. So with here we're going to loop through each file. We're going to do the same thing we did. So we're going to find the maximum departure delay across all our data. So we're just looping through the file names. We're reaching each file name into Pandas DataFrame, just with df.readCSV. We're calculating the maximum of each data frame. We're appending the maximums into a list, and then we're doing a final max. This is exactly what we did with the NumPy arrays. We could also wrap this read CSV with a Dask Delayed function, and then we'd be doing things in parallel. So this is how you could build a parallel Pandas using Dask Delayed and Pandas. So you could do that. And essentially all Dask DataFrame is all those parallel algorithms already built for you, mimicking the Pandas API, so you don't have to do that yourself. So if we did this loop, we would be able to do that. But now let's do this in parallel. Remember, DF here, let me go here. Remember, earlier we read in DF, and DF is a delayed data frame, a Dask data frame, and nothing's being computed. So now I'm going to time df.depdelay.max.compute. So this is the same thing you do in Pandas, but it's running in Dask. Okay, so this took a certain amount of time. It calculated the answer. So this kind of does the delayed computation for us and creates it. As with Dask Delayed and with a lot of the array stuff, we do need to call compute. Everything is done lazily. Dask will also delete intermediate results as soon as possible. And this lets us handle data sets that are larger than memory. And this also means that if you do another computation, you're going to have to load in the data each time. So if you, okay, so let's look at the visualizing of this and let's look at what it actually looks like. So if you look at the bottom, it split it into, so we had the 10 CSV files. Each CSV file is being read and it's getting the data from the CSV file and it is calculating the max. And so it's doing that for every CSV file. And then it's got all those maxes and it's aggregating the max across all of the files. And then it is, calculating your result. So this is the same kind of parallelism. Okay, so we have our DF. If you look, we have our DF. How would we get the length of this data frame? Let's see if you guys can do that. And so we're going to do two exercises. One is, how do we get the length of this data frame? Think of how you do it in Pandas, and then just do the same thing with this data frame. And if you guys think you know the answer, paste it in the column, and I'll try your code. This should be an easy one. Yay, someone got it. So it's just len of df. Len of df will calculate the length of the data frame. And then we did this earlier, so it's fairly straightforward. Someone else had another one. Let's try that one. So this works too. And this is because if you just type shape, we don't know the shape because we haven't read in the data. And that's why you had to do they did a shape of 0. If you look at shape of 0, it's just a delayed function, and a compute actually does the calculation. Okay, now this is a Pandas data frame, so you can do ordinary stuff. Oh, not Pandas. It basically, oops, that was bad. So these are all the columns these are the columns we have in our data frame, and there's one called canceled. So let's see, how would we work out how many non-canceled flights exist? So how would you do this in Pandas? Okay, someone asked, this is actually a good question. Basically, the df.shape, this does not work. Okay, this gives an error. And if you look, there's a reason for this. If you look at df.shape is a tuple. The first element is a delayed object. The second element is the number of columns, which we already know. So this is a tuple, and a tuple is not a Dask object. So you have to do a compute on this delayed object, which is why you do the shape of 0. And then that is something you can do a compute on, if that makes sense. Okay. So you know what? I will just show this because I think we're a bit low on time. We need to get to other things. So here we're using Pandas indexing. Cancelled is a Boolean. And so we can just say df.cancelled, and we will get the length of what's canceled. Okay. Now,
Perhaps we have a question on why you didn't have to call compute on length df.
yes. Okay. So again, the length is a special Python keyword that the length of a object is required to give, like the specification of the length function, it's required to give a number. And so Dask knows that, and it does the compute implicitly, because the way length is supposed to work, if length gave you a delayed object, it would break other things in the Python ecosystem. And so it's kind of something Dask knows. Length is special, so it does it. It's the way we implemented it in Dask. Okay. Actually, James, how are we on time? I'm not sure. Or Mike, do you know how we are on time?
Yeah, you're doing pretty good. You've got it's 12:30 now. You've got about 10 more minutes.
Okay. Okay, so we're going to do a group by example. And so let's see, I'm going to give everyone about 2 minutes to see if you guys can write a group by to see how many non-canceled flights were taken from every airport. So think of how you do a group by in Pandas to find the flights from every airport, and let's see if we can do this. And if you have an idea, paste it in the chat. Actually, while you guys are working on that, a couple of people are confused on this. Let me just show this. df.cancel.head. Let me just show you what it looks like. df.cancel.head is a Boolean, and so it just has a bunch of falses. If I put a tilde in front of it, it inverts it. So falses become trues and trues become falses. This is true for a lot of things like NumPy arrays, Pandas. This is just a fairly straightforward thing. So here, what I'm saying is keep the things where it's true. So basically, it's kind of saying where canceled is true, keep it. So, okay, so Stephen has a group by that we can try. Let's try it. So let's see. So what he's got he's filtering out if it's canceled or not. Then he's grouping by origin, and then he's counting the origin, and then he's computing. So let's see if that works. And it does. So great job, Stephen. Okay, if there's any questions on that, please ping, and I'm going to go to the next one. Now, okay, why does mean should work? Someone's asking why it shouldn't work for mean. It should. I'm not going to go into that right now since I'm going to try and finish the tutorial. But someone asked why mean didn't work, and it actually should. So we'll. Okay, now what's the average departure? In interest of time, I'm just going to show this one. Again, here, this is actually the mean one. So we've got a df.group by, we're grouping by origin, and then we're taking the depth delay column, and then we're calculating mean, and then we're computing it. And so this is the average departure display. Departure delay is the time it took for departure. So it's not a Boolean. It's a float, I think. Okay, let me just see how much more we have. I am going to go ahead and skip this last example, and I'm going to talk about sharing intermediate results. This is just another example that lets you group by the day, a week, and then do the mean, and you can look at that. But each of the computations we did earlier is doing everything from scratch. We're reading the data in from, a lot of the computations from scratch. And so we're not sharing things. And this gets inefficient when you're doing a lot of stuff. So let's look here. We have two different, we're going to find out how many flights were not canceled, and then we want to calculate the mean and the standard deviation of those flights. Okay, the mean delay and standard deviation of the delay for those flights. And these are delayed objects. Like if you look at these, this is a delayed object. We actually haven't done any computation. So now let's actually compute them and see how long it takes. Okay, and if we look at the time in a second. It's taking a few seconds to run through it. Okay, so this took about six seconds of wall time. Now we're going to call it a slightly different way. We are going to use unpacking. We're going to use Dask compute that lets us call a compute on both of these at the same time. And it will give us an answer in a tuple, and it'll unpack that tuple into these two. And if we do this, if we look, it's taken roughly half the time. This was almost 7 seconds. This is about 3 seconds. And this is because the first half of this is the same for both of those computations. They have to read all the CSV files. They have to calculate this filter, reduction, df cancel, tilde df cancel. And then there are some sums and counts which are duplicated between both. So if you want, we can visualize it. And if you look at it, this stuff at the bottom is common. And so it's doing it in common, and then it is getting the advantage of having a fair amount of this stuff done in common, so it's not repeating it. And again, Mike will go into the persist logic later, where we can use a specific command called persist. When you know that you're going to use something over and over again, you can kind of have it preloaded into memory. And so thinking about the way you do things can be important in terms of speeding things up. Okay, closing out some final things. Pandas has been around a lot longer than Dask, and it has a vast API that's increased over time. If your data fits in memory, just use Pandas. The Dask DataFrame module gives you a limited, but very, I find it very useful, like a subset of the Pandas experience, specifically for when you have data sets of computations that don't fit comfortably in memory or can take advantage of parallelization. So in this data set, we've done some stuff. We've used a small data set. It's about 45 MB or 400 MB in memory. In this situation, you'd never use Dask. There's no reason to use Dask for such a small data set. Dask DataFrame becomes really meaningful once you start hitting memory error, or once your kernel starts dying when you start reading data sets. We personally, in my line of work, we have used Dask DataFrame with data sets which include 20,000 CSV files or Parquet files on S3, multiple terabytes, really, really large data sets and things like that. And I'll throw a few other things out here. Getting back to the CSV and Parquet example earlier, some people were saying they love CSVs. One advantage of converting your data to something like Parquet is, let's say you have, this actually is a case right now. We have a client who has a data set with 1,600 columns, but they only need 5 or 10 of those columns for any particular analysis. If you have the data in CSV, you have to load all 1,600 columns. If you have the data in something like Parquet, you can pick and choose which columns of data you load and only deal with that. The other thing to remember with Dask data frames is when you do the final compute, it brings all the data into memory as a Pandas data frame. So if you create a Dask data frame that is based on 1 terabyte of data on disk, and you just say df.compute, it is going to try and bring that entire terabyte of data into memory, and you will crash your kernel. The use case of Dask data frame is you load a huge data set, and then you conduct various operations that reduce the size of the final data set. Like you do some filters, you do some group bys, you do some averages.
Darhas, I don't know if you're monitoring the chat, but we lost your audio. Can you guys hear me?
Yeah, I can't unmute Darhas, so I don't know if it's...
Yeah. James can hear me. Okay, others can hear me.
Yeah, I can hear you, yeah.
Can you hear me now?
Okay.
Yes.
Sorry, my headphone battery died and took me a while to work out how to switch to the laptop mic. Okay, also, Pandas does a really good job of releasing the GIL in certain applications. And so certain applications, you actually get a speed up and it can do those Pandas operations in parallel. I will say there are certain things which are inherently hard to do in parallel. A global sort is one of them. Drop duplicates on a global data set is another one of them. And group bys with 2 really large distributed data sets, merges with 2 really large, merges and joins, really large data frames is a problem. There's a best practices guide, which will fix some of those things, but some of those things are just fundamentally difficult in parallel. Okay, I guess, can you guys hear me okay? I guess some people are saying I'm still kind of out of sync. I think one last exercise we'll just walk through is we have some built-in built-in functions for Dask, but if you have for Dask data frame, but if you want to write your own function, and I don't think I'm going to go through this entire example right now, but this gives this section here gives you an example of a custom function that you might write in Pandas but isn't available in Dask. So if for example you didn't so dd.2time delta actually does exist in Dask, but if it wasn't, you could use the function map partitions. And what map partitions does is run a Pandas function or run a function on every partition. So if you wrote a function that took, let me get rid of this. If you wrote this compute departure timestamp function that worked on a single Pandas data frame, and if you wrote this, then so this is a function that takes a single Pandas data frame and calculates the time delta, like a timestamp. Now, you could use map partition to run this function on each individual Pandas data frame, each individual piece, and then combine them together. So if I do this, this calculates the date time. So this is kind of a way, map partitions is a way to write your own functions and then pass them in and have them run in a parallel manner across the entire data set. Again, I already covered this. I think that's about it for what I'm going to cover on data frames. I guess, James, I think we take a break now, and I think Mike is next.
James will be next for a little bit, but yeah, we take a break.
Okay. and we can try answering some questions during the break, I guess, if folks have any. Okay, we're going to do a 5-minute break instead of a 10-minute, so we'll start again in 5 minutes. And
Darhouse, if you want to stop sharing your screen, we can bring in James.
Yes, I will do that.
And you as well for a little bit to answer questions.
Once I work out how to share. Okay, there we go. Okay, if you guys can vote on the questions, that'll help a little since there's quite a few of them.
Yeah, please do.
Oh, is there actually, this is a good question. Is it possible to apply a lambda expression to Dask data frames? Yes, there is a dot apply and a dot map on the data frames, and that's actually usually the way you do it. Kind of the same method chaining logic that you would use in Pandas. So Andrew's question about setting up Dask on cloud servers and clusters. I'm actually writing a blog post right now on some better ways to deal with Dask workers and environments in the cloud. And so later this week, before SciPy ends, I'm hoping to write a blog post on some new tools we've built to help with that. But there are a lot of different things that come into play there. Okay, what happens if I use apply and a delayed function? Okay, so general rule of thumb is you don't mix Dask data frames with delayed functions. Those are two different ways of doing things, and they don't really interact that well. So, when you use dd.read.csv, can you use multiple patterns? Not directly. What you could do is use a glob with multiple patterns and assemble a list of files and then pass that
in. There's a question, when would you use Dask DataFrame versus Xarray? So there's an Xarray tutorial. I might have already happened. I think it is happening later. That I recommend attending. So yeah, Xarray uses Dask under the hood. So yeah, when you're using Xarray, you can also be using Dask sort of without knowing it.
Yeah, at a high level, Pandas, you use, well, was it Pandas and Xarray or was it Dask and Xarray? What was the question?
When would you use Dask DataFrame versus Xarray? So Xarray has nice things like dimensions and labeled axes, things like that. So if you want those additional features, I highly recommend using Xarray. I will say Xarray uses Dask under the hood.
Yeah, and Dask data frames is specifically for tabular data. Xarray is for n-dimensional data. So once you go into the third dimension, you're not going to be able to use Pandas data frames. So
that's great.
You need to use Xarray.
Yep, and Rich said Xarray tutorials on Thursday. Thank you, Rich.
Yes, and definitely plug for Xarray. That is a great project.
Yeah, definitely. Okay, there's a question. If Dask decides there is nothing to be parallelized, it will execute sequentially, right? In this case, will it be slower than versions without any delayed decorators? Yeah, so if there's nothing to be parallelized, meaning like every step in your computation depends on the previous step, there are no sort of independent tracks in your task graph, then yeah, Dask will just compute everything sequentially, just like you would normally without using Dask for parallelization. There is a small overhead associated with using like Dask tasks. So there is a small overhead that would make it in some cases slower than using, not using Dask, just running things synchronously. However, the overhead is small. So you won't be noticeable unless you're using lots and lots of delayed tasks that are completely one after the other, and nothing can be parallelized.
There's a memory warning question related to garbage collection in Dask, and asking for recommended ways for tracking that down. I'm actually going to cover that in a moment in the advanced distributed section. There's a bit about debugging there.
Someone's asking about overlapping chunks, and we do have overlapping chunks. It's just a different API call, right?
Yeah, there's a map overlaps function in Dask array, which will allow you to do overlapping computations involving overlapping chunks. Okay, so I think we are about 5 minutes, so let's go ahead and start the next notebook. Let me share my screen real quick. Too many video sources. Oh, great. Okay, so Darha's just dropped off. Let me try again. All right, so the next notebook is notebook 05_distributed. So this notebook here, and let me go ahead and increase the font size real quick for everyone. Hopefully that is big enough. So far today we've been basically constructing Dask graphs using a few different APIs, using the Dask Delayed API, the Dask Array API, and the Dask DataFrame API. And then we've just been calling compute on those objects, or maybe we're calling Dask.compute on several of those objects and haven't really been worrying about anything else. We just said, call compute, it computes the result for you. So now we're going to sort of step back and start talking a little bit about what's happening under the hood there. So what's happening is Dask schedulers are actually going through your task graph and computing the various tasks. So back in the delayed notebook, do this increment function, then this other increment function. After that, go ahead and pass those results to an add function. And it's doing that by submitting tasks to different like resources. There are 4 different types of schedulers that are available in Dask. So there is a multi-threading scheduler, which uses a standard thread pool, a Python thread pool from the standard library. There is the multiprocessing scheduler, which is backed by a multiprocessing pool in Python, a single-threaded scheduler, and that just executes tasks in the main Python process. So there is no parallelization happening when you use the single-threaded or synchronous scheduler. And then there's also the distributed scheduler, which we'll talk about later in the notebook. These first 3 are generally, like you'll often hear them referred to as single machine schedulers. These are sort of the first iteration of schedulers, and they require no setup. The dependencies are just a Python standard library, whereas the distributed scheduler, while more advanced, does have additional dependencies like Tornado. So how do you go about choosing between one of these different schedulers? So there are a few different ways you can do that. The sort of most granular way you can do that is in individual compute calls. Before, we would just call compute with open parentheses and wouldn't provide any input. There is a scheduler keyword argument that you can specify to select a different scheduler. So you would pass in, for instance, if you have some computation you want to do, compute scheduler equals single threaded. That would then use the single threaded scheduler. You could change that to be processes, and it would use multiprocessing, threaded, multi-threading, just for that particular compute call. You might, however, want to set the scheduler for like a given block of code. Like I'm going to call compute on a few things, and I want them all to use a certain scheduler. So for that, you could use there are a couple ways you can do that. You can use the dask.config.set context manager and specify what scheduler you would like to use. And then inside that block of code, inside that with block, any compute calls will then use the specified scheduler. So in this case, I've said scheduler equals processes. So use the multiprocessing scheduler. And any compute calls, there's only one here, but if we had multiple of them, they would all use the multiprocessing scheduler. And then when you exit the with block, when you exit the context manager, then we'll go back to just using the default schedulers for the different collections. Additionally, you may just want to globally set it. And you may want to say, I don't care about a particular block of code. I just want everything to use a particular scheduler. Then you can still use dask.config.set, but don't use it as a context manager. Instead, just call it directly. And then any compute calls that happen after that will use the specified scheduler. In this case, it will be the multiprocessing scheduler. One thing, I guess, that we're not covering here, I'll show real quick, is if we wanted to, so say we have my value.compute, and I want to use the multi-threaded scheduler. So I think threaded, yeah. I use the multi-threaded scheduler. By default, what this will do is create a thread pool that has a number of threads equal to the number of cores on your machine. Earlier, I had said that you do, however, have the freedom to specify the number of threads you would like in a thread pool, or the same for processes in a process pool. You can do that using the numWorkers keyword argument. So by default, it will choose, if you don't specify numWorkers, it will choose the number of cores you have as the number of threads or processes. But you can also tailor that to your specific needs. Okay, so let's move on. We'll go ahead and load in some of the flight data. Again, if you're running on Binder, you may want to add the --small. And we're just going to set up some computation here. We're going to use Dask DataFrame's read CSV to read in all the flight data CSV files. We're going to parse dates. We're going to set some D types, and then we're going to perform some computation. Here, we're going to find the maximum average non-canceled delayed time that's grouped by airports. That's a mouthful. So the main, this is sort of similar to what we were doing earlier in the Dask DataFrame notebook. The main point here is we're just setting up some computation that we would like to run. So now what we'll do is run that particular computation using each of the different single machine schedulers. So we'll first run with the multi-threaded scheduler, then the multi-processing, and then the synchronous scheduler. And what we'll do is we'll get the time before the computation, the time after the computation, to figure out how long the actual computation takes. And then we'll print that to the screen along with the result that we get for the actual computation. So we can see here the multi-threading scheduler took just under 4 seconds, and the result 10.35. The multi-processing scheduler took 10.6 seconds, same result. Synchronous scheduler, 6.2 seconds, same result. So the take-home point here is that these different schedulers will all give you the same exact result. So we're getting the same result each time. It's going to go through the Dask graph and submit tasks to various resources. But you're always going to get the same result, just with slightly different performance characteristics that could be important depending on your particular application. So you can see here the difference in the performance characteristics. Like for instance, the multi-threading scheduler is taking, a lot longer than the multi-threading scheduler. So you might ask yourself, like, what are some rules of thumb here when picking between threaded processes and synchronous scheduler? So let me just say initially, the synchronous scheduler is used primarily for debugging. There is no parallelization associated with the synchronous scheduler. So good rule of thumb, if debugging, which Mike will talk about later, you feel free to use the synchronous scheduler. It's nice. You get nice tracebacks and things like that. When picking between threads and processes, what you want to do is think a little bit about the actual functions and computations that are happening in your task graph. So when using a thread pool in Python, Python has the global interpreter lock GIL, and that means that say you have a thread pool with 10 threads in it, only one of those threads can actually execute C Python code at any given time. So if you're running a lot of code that is holding on to the GIL, then you won't get a good performance there. You won't be able to parallelize very effectively. However, lots of libraries, libraries in the SciPy stack, like NumPy and Pandas, release the GIL in most places. So you can use the multi-threaded scheduler safely when using things like NumPy and Pandas generally. If you are running lots of code that holds onto the GIL, this would be something like, for example, you're doing string manipulations in Python that will hold on to the GIL. Then you might consider using the multi-processing scheduler. That's because the processes in Python can run C Python code in each process concurrently. So that's sort of the advantage of using processes. However, the disadvantage of using processes is there is serialization between processes. When using multiple threads, they all have the same shared memory space. So you can effectively just pass around pointers to intermediate results and dependencies that are needed for other tasks. There's no serialization cost there. However, in multiprocessing, you have to pass dependencies between processes. So you have to serialize some piece of data, pass it to another process, and deserialize on the other side where it can then be used. So if you have lots of that communication, you'll also slow down your performance there as well. So there's some balance here between communication costs and holding onto the GIL that you'll need to sort of put some thought into and kind of maybe experiment with as well. There's some additional information here in the Dask documentation about choosing different schedulers. Again, thinking about serialization and the GIL.
James, can you run visualize on that just to?
Oh, sure. Yeah, definitely.
That might help. And we've got plenty of time, so that's what I'm.
Sure.
And we've also got some questions.
So here we go. Yeah. So we're seeing we are getting some these portions here are all independent of one another. So these can all be run in parallel easily. But then we start getting these intermediate results. You see all these arrows pointing to this circle or this circle. So to execute this task, we have to wait till all the other arrows that are pointing to it, those tasks are done before moving on to this task. So this is not embarrassingly parallel. However, there are opportunities for parallelization here. And there's our little final result at the end. Okay.
What I liked about this graph in this context as well is that it is showing the communication overhead, which explains why we're seeing speed ups between the sync and the multiprocess. And you talked about the communication overhead that you have there with multiprocess. You're seeing that here with the graph.
Yeah, exactly. So what Mike's referring to is just looking at this circle right here, this particular task needs a bunch of inputs to call this function. Each arrow that's passing to this is a different input to this function. And it could be that these intermediate results that are getting passed into this function actually were computed on different processes in a process pool, in which case, say this, it's probably not, but say this is a little data frame here. We would need to serialize that data frame, send it to another process, deserialize it, and then we can finally pass it to this task for execution. And that's the communication cost that Mike's referring to there. And you can kind of see it with all the arrows pointing here to this particular task in the graph. So yeah, highly recommend checking out the task visualization. If your task is not, thousands and thousands of tasks, otherwise we'll run into the problem Darhas did where it was super tiny when trying to visualize it. Okay, so maybe I'll go over and do we have any other questions that are pressing right now that are related to this? Okay. Let me go ahead and carry on then for the time being.
Is for multiprocessing, is it single threaded, each process?
Yes. Yep. For multiprocessing, these are, we'll talk in a second. Distributed, you can do multi-threaded processes. Here we're having either a sync for the multi-threaded scheduling. There's one process with multiple threads. For the multi-processing scheduler, there are multiple processes which are each single threaded. Great question. Hopefully that answers it. Okay, so that's it for the single machine schedulers. So we'll now move on to the distributed scheduler. So although the distributed scheduler is called the distributed scheduler, it does scale out to multiple machines. It also works perfectly fine on a single machine. So perhaps a better name for it would have been an advanced scheduler as opposed to a distributed scheduler. What the distributed scheduler consists of, distributed cluster consists of, are one or more worker processes. These workers are where the actual tasks get executed. So going back up to this graph here, each of these individual tasks in our graph are executed on workers, and there can be one or more workers. Then there is a single centralized scheduler that maintains basically the state of the cluster. So this will keep track of what tasks you've asked to be computed, the dependencies between all the tasks. So in our visualization up here, it'll keep track of basically all these arrows that are linking different tasks together. It'll keep track of what tasks are complete, which ones aren't, which ones are pending. It will also farm out the tasks to the different workers to execute. To execute them. So the scheduler sort of controls the state of the cluster. The workers actually do the work. They actually execute the functions. And then there is an additional client, which connects to the scheduler. And that's sort of the user-facing object that you use as a user of Dask to submit tasks to the scheduler. So you will create a client that will then submit tasks to the scheduler. The scheduler then handles everything else. It handles farming out tasks to workers. When the workers and everything have computed your tasks, you can then request a result using the client, and the scheduler will take care of pushing that back to you. There are lots of ways to deploy a Dask cluster, a Dask distributed cluster. As I said, you can deploy it locally on your laptop using local processes and threads. You can also, let me click here on this deploy link. There are lots of other options here. You can deploy using the command line. There's an SSH option. You can, on HPC systems, there's a project called Dask Job Queue for that. You can deploy on Kubernetes or Yarn, Hadoop. There are lots of ways to go about actually deploying Dask. We're not going to go into those here. They're sort of out of scope for us today. Instead, what we're going to do is the simplest one, which is we're going to run a Dask distributed cluster locally. So we are going to be using local worker processes, and our scheduler and workers are all going to be on local processes on your laptop. So to do that, all you do is from dask.distributed import client, all you do to create a local cluster is instantiate the client without any additional input parameters, without any keyword arguments. And what that will do is create a local cluster here on your laptop. So it will by default choose the number of workers to be 1 per core. So for here, I have 4 workers. Notice that the workers are multi-threaded. So each worker has 2 threads in it. So that's why we're getting 8 cores here. There's a nice little, the distributed cluster has nice features like you can scale up the number of workers. So I'm not going to do that here, but you could easily scale up the number of workers or scale them down. So that's how you instantiate a local cluster on your machine. So here it says if you're in Jupyter Lab and not using the Dask Lab extension, be sure to click this dashboard link here. That is one of the big advantages of using the distributed cluster is it has advanced diagnostics. So let's go ahead and click on that here. So this brings up a separate, this actually is we're running a bouquet server on the scheduler as well as all the workers, and we collect state and push it up to these bouquet plots. So we can see this is the status page. Right now there's nothing on here because we're not running anything. We'll see this be populated when we start running things. Here is a worker tab. We can see here are my 4 workers, each with 2 threads. Notice this is updating live. Like we can see the CPU usage and the memory usage. So this is the current status of our workers. So this is one way to view things in a separate tab in my browser here. I actually have installed the Dask Jupyter Lab extension. So what that allows us to do, we have this little Dask tab over here. That allows us to bring some of these diagnostic plots into and embed them into our Jupyter Lab session here, which is really cool. So totally fine to view it in a separate tab if you prefer. I'm just going to render them here using the Jupyter Lab extension in my notebook. Okay, so let's go ahead and start using the distributed cluster now. So what we're going to do here, this should look very similar. This is almost copy and pasted from the delayed notebook. So we're going to have an increment function, a decrement function, and an add function that do what you think. They increment, decrement, and add. There are just these added sleep statements in here as well to sort of simulate some work being done. So we'll define these functions, and then we'll go ahead and do sort of a standard Dask delayed workflow here, where we delay our increment and decrement and add functions, and then do some computation and call compute. And what we'll see is over here, we've started to do these computations. So we can see our task room over here. This is the decrement function happening. This is the increment function happening. And then we have our add function happening. So what happened here, notice I didn't tell Dask to use this distributed cluster. Whenever you instantiate that's because when you instantiate a distributed client, it will automatically register itself as the default scheduler. So after this point, unless you specify otherwise, the distributed cluster will be used. Like for instance, if I said here scheduler equals sync, that then will use the synchronous scheduler, but otherwise it'll use the default, by default, it'll use the distributed scheduler. So what we see over here is this axis on the x-axis is the time axis here. We can see here's my decrement function. It took 3 seconds. Let's go up here. That corresponds to the sleep 3. Then here's my increment function, took 5 seconds, corresponds to the sleep 5. And notice those ran in parallel. So we were able to run both of these in parallel. And then after both of these completed, we then were able to run our add function, which took 7 seconds, which is consistent with this sleep 7. If you look closely, you'll notice there's a little red sliver here between the green and the blue here. I don't know if I can quite get my cursor on it, but what that is, that is a transfer. So we're transferring a dependency. In this case, we're transferring the result from the decrement over to this process, this worker, so then we can then use it in our when we execute the add function. So we're getting both parallelism here with the distributed scheduler as well as this dependency management here. And there's a nice way to visualize it in the task graph. So let's move on to a slightly more complicated or involved example. So we're going to go back to the beginning of the notebook where we had that DataFrame example and run that on the distributed scheduler. So here you can see there's many more functions that are happening, and that happened pretty quick. I can run it again in a second. But here we're seeing, here's all of our read CSVs happening. Then all these little, they're kind of color coded by what function is getting called here. Here's a group by, sum on a chunk. Here's another one. Here's a group by count on a chunk. And then you can see here, this red, that's a transfer get item. That means we're transferring some dependency from one worker to another because another worker needs it for the computation it's trying to do. Notice there is not a lot of red here. So Dask distributed in general is quite intelligent about how it does computation. So it thinks a lot about data locality. So we'll try to minimize the amount of data transfers possible. So if there's a particular worker that has several dependencies needed for another task, it will then run that new task that requires those dependencies on that worker that already has that data locally to avoid a transfer between workers where possible. Okay, great. So yeah, there are some other links here about the architecture for the Dask distributed scheduler, as well as a link to some diagnostics information about the dashboards. So that's sort of the introduction to the distributed scheduler. For this exercise, there are a few DataFrame computations here that we can run on the distributed cluster. So the point of this exercise is not so much the actual computations happening here, but rather kind of exploring the Dask dashboard here. So you can go into, if you're using the Jupyter Lab extension, you can go and check out these different types of plots here. So here's a CPU one, and if you're not using the lab extension, totally fine. You can use the dashboard link in a separate window to maybe put the notebook and the dashboard side by side so you can see what's happening. So yeah, sort of experiment with the Dask dashboard here, and then Mike and myself can answer questions in the meantime.
Also add to connect to that dashboard, you've got to copy and paste that URL into the extension. Some folks were asking about how to do that.
Gotcha.
You showed it, but you know.
Yeah. Sorry about that.
Yeah. No worries.
Yeah, someone also mentioned the client repr in Jupyter. If you have a client instantiated, if you just output it in Jupyter, it will have a dashboard link on it, which you can just click and it'll redirect you. How to reset zoom in bokeh plot. There should be a reset button. It looks like a little circle with a couple arrows in it, I think. Let me pull that up.
Yeah, looks like a refresh button.
Yeah, like a refresh button. Yeah, click that and it should pull you undo the zoom you've done. Yeah, so for the Jupyter Lab extension, you'll want to, depending on how things are set up and how things are set up, like on Binder, we have it set up to pull the correct address right away. You do need to pass the address for your dashboard into the upper left-hand corner in the Jupyter Lab extension. Paste it there, and then the lab extension will then be able to connect to your cluster.
Is there a rule of thumb when provisioning resources for estimating scheduler requirements to manage the worker process versus threads? So I guess to answer that, I would look at the example that James showed in the beginning and look at those different schedulers and think about the different paradigms there. So it boils down to your trade-offs between communication overhead between processes, as well as you'll see that in a distributed cluster between nodes in that case versus multi-threaded and McGill and releasing that for different computations. So generally, the rule of thumb, I believe there's also a docs page on this. Do you have that handy, James?
I don't.
I'll pull it up real quick and throw it in the chat.
Yeah, so I noticed sorry, I must have missed this. There's a question with a lot of upvotes. So Dask looks great in these tutorial examples, but what are the limits of Dask that one should consider when using for real world analyses? Yeah, so great question. Yeah, the tutorial we're going through rather small, sort of like more illustrative examples, but we're trying to allude at some of the, I don't know that I'd say limitations, but some of the things to be aware of when using Dask. So, things like balancing the number of threads and processes, this has come up a couple times already, right? So for your particular workload, you'll need to think about, are you holding the GIL? Are the things you're running holding the GIL often? Are there lots of different communications happening between processes? So those are definitely things to consider whenever you're creating your distributed cluster or any of the other schedulers as well. Another thing to think about that's come up is with the, we see often people having issues with the chunk size in Dask arrays or the partition size in Dask DataFrames. That's also something to tune a little bit, depending on your particular, the particular resources available in your cluster. So you'll want to make sure that you can fit a few partitions or a few chunks in memory pretty comfortably. And yeah, also you may end up running into, if you have lots of super tiny tasks in your computation, there is some scheduler overhead associated with each task. So over time, that will build up if you have a large million or order million task graph. There are some ways to go about helping alleviate some of these issues. So for instance, on a Dask array, you can re-chunk a Dask array. So if you have lots of little tiny chunks, it may be advantageous to re-chunk to have a larger chunk size, so you'll have fewer tasks in your task graph. Mike in the next notebook will talk about persisting data sets to Dask collections to distributed memory. That's also incredibly useful in helping avoid having to redo lots of computations over and over again. So those are some sort of things that users run into commonly and some potential solutions for them. Also, I see Rich said, love the cluster map. Totally agree, Rich. It is very cool. It shows all the communication between the workers and the scheduler. It's thank you, Jacob Tomlinson.
I have to shoot. This is the first time I've shared my screen, so I have to change some settings. I'll be right back.
Okay, sounds good. I'll keep monitoring the questions. Yeah, so the next question is distributed.worker warning, memory use high, but worker has no data stored on disk. So Mike will talk a little bit about debugging different warning messages like that in Dask Distributed. That said, there is a known memory leak in NumPy that can result in this type of thing as well. So that's also something to be aware of. That's not necessarily an issue with Dask, but more, like a memory leak in NumPy.
Yeah, I'm back.
Hey, welcome back.
All right, I'll share my screen now if we're ready.
Yeah, no, I think so.
All right, hopefully you can see my screen now.
increasing the text just a tiny bit.
All right.
Yeah, that looks good to me. Hopefully it does for others too.
All right. Let me know if anyone can't see. Okay, so switching over to advanced distributed. So up until this point, we've been submitting computations by calling compute, mostly using either delayed or some of the higher level APIs have been implemented, such as Dask Array, Dask DataFrame, etc. So in this part of the tutorial, we're going to kind of drop down to a more advanced or lower level interface called Dask Futures. Futures, this is an alternative to compute, but it's derived from concurrent futures. So if you're familiar with those, it's going to look fairly similar to you. So as we go through this, one of the things, the way that you can submit, one of the ways that you can submit or create a future in Dask is if you have a client, you can call submit on it. You can give it a function and any arguments that would go to that function, and you'll get that future back. So that's what this example is here. So just one moment while I spin up my local cluster again. Okay, and you can see I have the dashboard over here on the right, so we'll be able to see stuff as we run computations. So this is that familiar increment method that we've been dealing with before, only instead of using delayed here, we're going to use submit to create a future. And so one of the interesting things here is we're using that client, we're passing the reference to the function and the arguments, and when we create the future, it returns immediately, but you see that we get some additional information here. We get a status of pending, we get a unique key, as well as like the name of the function. These statuses actually change over time, so we can see actually by looking at the task stream that it's already completed. So now if I try to access this feature again, I'll see that its status has changed. It's no longer pending, it's finished. And it actually has a type because we've now returned a value for it, and Dask knows what that type is. It's the built-in int. So that's essentially what we're going to be talking about here a little bit with the features interface. There's some interesting alternatives you can run here besides just returning the future. You could call, I'm going to add a cell here. You could call wait or progress, which would return a progress bar. So I'll show you what that looks like, and we'll see a little bit more of that here in a minute. Oh, yeah, I have to import it. One moment.
Mike, could you increase the font size just like one more click?
Sure. Thank you.
Thanks.
Hopefully that's better. Run that again, and we see we've got a similar progress bar to what we have in the dashboard, and it's complete like it is over there. Alternatively, we could call wait, and this would essentially notice how when I submitted this this function and got that future, it returned immediately. If I and let me call it again here so we can see that it has indeed finished. Great. If I were to call wait on this, now that I've got this imported, this will work. The cell actually will not return immediately. It happens very fast. I have to, because I didn't change it, that's right. Change this to 2, so it will resubmit. Well, that's not working for me. Wait is returning immediately. I don't know why. Do you know why, James?
It looks like the task is finished.
Yeah, I think it's just been, I don't have a sleep there. We're used to our sleeps. So that's what's going on.
Yeah.
And I believe we have some of this down below, but this is fun. Sleep for 1 second. Run that again, and now we see that the cell blocked for a second, which is what I was trying to show there. So that's the features interface in a nutshell with the progress and the wait. We've also got this other function on the client called gather. And I believe I can call that here and it will return immediately because the task is complete. But we actually get the result now as well. This is equivalent to on the future, you can call result if you'd like. What you can do with the gather interface is you could actually have multiple futures here to get those back, kind of like calling dask.compute or client.compute on multiple delayed objects.
Mike, could you maybe, there's several questions about, could you explain a little bit more about what a future is?
Mm-hmm. So essentially you can think of a future as if you look at the, essentially it's the same as the concurrent futures interface, but essentially you can think of it as a reference to a task or a object that's going to be completed in the future, right? And it's essentially not a value and it has a status. There's an asynchronous computation that's going on the Dask cluster. Whenever that computation completes, the status is updated and the value is there. So hence the name future. It is a reference to an object that will have a value once the computation is complete. Does that make sense?
Yeah, no, I think so. We can see if other people have follow-up questions. Thanks, Mike.
I can't see the questions right now as I'm sharing the screen. So let me know if there's any that come in.
Yeah, I think we're good for now. Thank you.
Okay, cool. So now let's go back to the example that we've been working with from delayed here. So I'll go ahead and run this. This should be pretty familiar to you guys at this point, just using the delayed interface. And we're going to call compute on that. And this time we're going to reference this as that future. And we'll actually see the work being done on the dashboard. So notice how that returned immediately. We can call gather to actually get the result. That will wait until the result is ready. Let me run that again. Oops. And while that is running, you see that it's waiting. And there you go. So this is a way of calling compute on delayed functions and returning the results using the futures interface. As I said before, we have the client submit to. Go ahead.
Oh, sorry. I was going to say there's been some questions about Dask futures versus Dask delayed because they look somewhat similar. I just wanted to really quickly say the difference between the two. So they are somewhat similar. I mean, we're just like in the distributed cluster, we're submitting a function to be executed. And in Dask delayed, we're delaying a function to be executed. So from that perspective, they're quite similar. The main difference is that when you create a delayed object, nothing has happened other than you create the graph itself, the task graph itself. No computation takes place. Whenever you create a future, it's an asynchronous computation. So you submit a function to be executed on the cluster. It returns a future to you to hold in your Python process. And that computation does start right away on your cluster. So that's the main difference. Delayed computations, the computation doesn't start until you call compute on it. Whereas with the distributed cluster, when you call submit, the computation happens asynchronously on the cluster and you get a result, a future that points to that computation. And whenever that computation is done, you can then call results and get the actual result from the function. Hopefully that helps. Sorry to interrupt, Mike.
No, that's great. Please do. And so this is what James was just now talking about with client .submit. We're submitting a function, and notice now this is the inc function itself that's not a delayed object. and an argument to that function. So now we're going to go through an exercise where we'll take the delayed example from up here, and we're going to implement it using only Dask features. So we'll wait a few minutes for folks to do that, and they can essentially grab the code up here. We actually don't need to define the functions again, but the logic will be something similar to this. Rather than using delayed, use this client.submit interface. And James, if you could let me know if there are any questions that come in while folks are working on that.
So there's a question, what are some examples of cases where you'd want to run a future versus chaining up operations with delayed and then running compute? So for that, for instance, like for very dynamic workloads, you may need to submit new tasks based on the output of some tasks. So like, for instance, say you have one computation that runs, and then based on the output of that computation, you then may or may not submit other tasks dynamically. So you compute some value. If it's greater than 100, submit these tasks. If it's not, submit this other different set of tasks. And the futures interface allows for these more dynamic workflows. So that's one way in which you would, that's one particular use case in which you would want to use futures over Dask delayed. And then, yeah, also there was a comment about delayed being able to operate on results implicitly. Futures require you to wait on results before operating. You can also operate on results of futures, like you can use a future as an input to another future, and that will totally work. It will build up that dependency. This future requires this one to be done first, and that's the input to it. You can build up those task graphs using futures as well.
All right. Doing more time on this exercise, I'll show the answer in the interest of time. But essentially what we're doing is we're replacing all the delay calls with client.submit calls. And then calling gather on the end. Run that. Okay, so now we're going to go into another example. If you haven't ran this, hopefully everyone's ran this at this point, go ahead and run the prep.py to download the accounts and prepare it. So here we're going to use, this is actually using Dask Bag, which we didn't talk about, but we're going to iterate over a list of all the accounts. We're going to load those files into a Dask Bag, and this will just pull out the lines. We can then call map on that bag to parse the lines. In this case, we're parsing with JSON to return JSON objects. And then we're going to do some filtering, pulling data out, and flattening, do a computed mean, and we're going to submit this all as a Dask future. And so while that's going, we'll see stuff get updated on the right, called progress. If we call that, we'll see all of those individual functions that are being called, and then call gather to get the actual results. And so that's an example of how you can use a future to do something a little bit more complicated than what we've seen before. And then to delete features, Dask features, you essentially just use the del command keyword in Python, which will free up that memory on the cluster.
question about, so does the client cache previous results? For instance, running client.submit inc1 immediately finishes the second time it's been run.
Yeah, we saw that earlier when I got confused. So if I hit submit up here whenever I was submitting futures more than once, if it was already returned, we'll actually just get the results. So client.submit would do that here, for example. Notice how it's finished.
Both the function and the inputs to the function to get some token on the future. And it will check that to see if you've already submitted a task with that same function and those same inputs before. And if you have already submitted that task and it's it won't resubmit that task, it'll say, oh, that's already been submitted. Whenever you ask for the result later, it will just pull that out. So it won't resubmit that same task if the function and the inputs are still the same.
All right, I'm going to move on if there are no further questions. So we're going to cover persist here. So go ahead and run the prep.py to generate random data in this case. We're going to load that data using HDF5. We're going to load it into a Dask array using the Dask array interface. And we're going to perform a sum. We're actually going to do it twice because we want to demonstrate the fact that we're pulling this data into memory, whether it's on a distributed cluster or locally here. Each time we call that compute, we're going to, it's going to take around the same amount of time. I'll go ahead and run it here. And that's because we're pulling the data into memory each time to do the computation. And so we got 6 seconds, should see around that. 6 or 7, yeah. So it's more or less the same amount of time because each time that we call compute, we have to pull the data back out from the disk here whenever we run through all of these computations in the test graph. Instead, if we wanted to, we could persist the data once we've loaded it into the cluster, or in this case on RAM. So I'll do that now. Okay, we can see the amount of bytes stored on my cluster. And if I call compute, the first time it should take just as long, and the second time should be much faster. So a bit faster. So I've noticed that sometimes it's not as fast as I'd like it to be. If you play around with the chunks, actually, you can get that to work. But it is faster, so that's good. All right, so quick exercise. Now that I've persisted the data that I've loaded from the file onto my Dask cluster, how do I release it? So I'll give you a few moments to think about that. If you want to post your answers in the chat, we can try it out. But I can't see the chat, so I don't know why.
Oh yeah, there are some answers being posted in the chat. Lots of people are proposing del X. Someone else posted future.release, parentheses.
Like that?
So yep, someone proposed that.
So no, it actually is del X. In this case, and you can see the byte story goes down.
There we go. Yeah. So just to kind of piggyback on that right there, the distributed scheduler implements garbage collection for all of everything that lives on the cluster. So whenever there are no more references to a particular future, it will then be garbage collected and cleaned up on the cluster. So here there is this X object in a local Python session that Mike created, and it was lived on the cluster, did some computation. Then when he did del X, there were now no longer any references in the current Python session to that variable, so that which is a future. So then that future got garbage collected and deleted from the cluster.
All right, so moving on, one of the benefits of this interface is it offers asynchronous computation. So unlike the delayed interface, as James was alluding to there, whenever we submit a function and return a feature from the Dask client, notice how we were getting the status as we polled that feature object. Essentially, we can get status on the computation as it's being performed on the remote cluster. We can also have results returned as the features resolve and actually get results and do things with those. So in this case, we're going to demo a feature that we're going to submit using this Rosenbrock function to return points and scores. I'm not getting into the details of that function. I'm sure some of you know that. But in this case, this is the function that we're going to submit. This is kind of equivalent to our inc and add and decrement functions from before. In this case, we're going to use this in conjunction with a bokeh visualization. So I'm going to load that. Essentially, we've got some an X and Y value. We've got a background that we'll see in a moment. And then we're going to get into our actual work. So what we're going to do essentially here is we're going to start at 0.00 as like kind of an initial guess. And as we run this Rosenbrock calculation, we're going to get kind of an approximation of trying to zero in on a optimal value, essentially. And so we're going to start off with some X and Y's. I'm not going to get into the plot stuff here, but here's actually where we're going to submit the feature using our function on our X's and Y's. And then this is another function that we haven't really talked about too much, but that's in Dask distributed, called as complete. And essentially what this is going to return is the features as they complete, as it says, and we'll be able to iterate over those to do something with those results. And so we'll submit, we're going to be submitting these features 10 at a time, and as they return, we'll do some post-analysis with them. So in this case, we're going to grab the result, which is going to contain the points and the score. We're going to look to see whether or not this score is better than the previous scores we've got. We're going to print it out if it is. And then we're also going to update the plot here with the code here. And then we'll submit more work essentially to the Dask cluster until we kind of reach some threshold in which we'll break and kind of be done. So as I run this, we should see the visualization appear, and we'll see it actually update as we're computing on the cluster. And it zeroes in on that optimal value. And this, by the way, if this is not working for you, this is one of those Jupyter extensions, the bokeh extension that we asked for you to install, but we didn't get that into the instructions until later. So hopefully you pulled that down early this morning, or we got that working. So zeroed in there on that value, and it should stop in a moment. We'll see our points come through here, and we see that around 1,1 is that optimal space. So that's an example of using futures for asynchronous computations, processing the results asynchronously, and updating a visualization. Any questions on that? All right. So I'll move on to debugging. In the interest of time here, we're almost at 2 here. So we had some questions around how to debug. So we've got a toy example here of a division, and what can go wrong when we divide by 0. Essentially, we get for that ratio delayed computation, we'll get a division by 0 error. So essentially, what we're going to do is zip over those values, compute that ratio, and then compute the sum. We're going to return this as a Dask feature. So I'm going to run that. And here we're using delayed as the decorator syntax rather than just wrapping the function. And this should return just fine. Okay, so we get a result of 11. But if we have bad input into this calculation, so here we've got a 0 in our B column, and we're dividing here. So we will get a division by 0 error. And so, yeah, we get a traceback, division by 0. So you can see where the exception comes from in the traceback. Fairly reasonable here. So this is essentially like what you'll get by default, and what we're going to look through, what we're going to look for as we go through these different scenarios below. So in this case, this is the exception. We got it, but you don't always get this. So say here, I'm going to run with a process scheduler. And we get this kind of weird cryptic error message. Oh, sorry, repeat process. We actually get a nice error message that tells us what value we need to enter. All right, and so since I'm on the local scheduler, I'll get a nice error message, but if I was on the distributed scheduler, I would not get that. So we're calling compute here on this scheduler because we want that one. Okay. And so you would want to essentially set this so that you can get the error message to debug. Another option in that scenario, let me rerun that to make sure that works. Sync, okay. You can use the magic command to get a debugger, which is really nice. So we can actually look at B here. And see that where B is 0. And so one of the problems here is if I'm running, you can imagine if I'm running this on a distributed cluster, we have a large computation. You don't want to run the whole thing locally, obviously, because it won't work in the first place. So one of the things you can do is we have on the client this recreate error locally method, which will give us that traceback. And we can use the postmortem debugger here too. And then, if all else fails, we can actually use the client to inspect the scheduler and the tasks. And you can look at the docs. There are all kinds of there's all kinds of information that you can pull from this. But here, what I'm going to do essentially is I'm going to loop over my scheduler's tasks, and I'm going to look to see if there's an exception, and then just print the state as well as the key, which will be the name of the task. And so we can see that ratio errored. So maybe there's some esoteric error. You can dig down and figure out what task is failing, and then start to inspect that. You can do other things. You can run arbitrary tasks on the workers or on the scheduler to try to see what's going on there as well. But there are some really good docs on that. So that's most of the advanced distributed notebook. Are there any questions before we move on to machine learning? We only have 10 minutes.
Question, although I wasn't quite sure what was meant. Is the memory taken when client.submit until we use client.gather?
On the cluster?
I think what you're, feel free to update the question or respond in the chat if I'm not answering your actual question. But what I think you're asking is memory taken up when you submit something until you call gather? I guess I should just say what does happen is when you submit a task, it'll get submitted to the scheduler that then gets farmed out to a worker whenever it's ready. And that result will stay on that worker until it's garbage collected. So you can call client.gather and that'll transfer the results like the actual, say you do some computation, the result is 5. It'll then, when you do client.gather, it'll then transfer that result, in this case, the integer 5, to your local Python session. But that future is still going to live on the worker until references go away. So you need to delete all the futures that are associated with that, like that particular future, to free up the worker space. I think that's what was being asked in that question. Yeah. Feel free to update.
And that's somewhat tricky because you may have multiple references to that same future in your notebook or in your code somewhere.
Totally. Yeah, so it's tricky in the same way that like garbage collection in Python, it can be tricky sometimes.
All right, in the interest of time, I'm going to switch to the machine learning notebook. Oh, nice. I can do Chrome tab. Let's try this. All right. Hopefully you see the machine learning notebook. Yeah.
Could you bump up the font one unit? Looks real good. Thanks.
All right, great. So we've talked about Dask Delayed, Dask DataFrame, Dask Array. We've talked about how the features interface. What we're going to talk about now real quick is another kind of high-level library called DaskML for parallel and distributed machine learning. And this essentially is following the, in many cases, you can think of it as a Scikit-Learn for distributed machine learning. And so there are many estimators and routines that have implemented Scikit-Learn that have been re-implemented for Dask objects. There's also a way, whether it's a distributed algorithm implementation, or whether it's just a Scikit-Learn-like implementation that operates on Dask objects like Dask arrays. And so there are kind of two different types of scaling that we want to talk about here. This is a great diagram created by Tom Osberger that talks about the two different problems that we're dealing with here. So we're typically bound in many computing paradigms, and especially in machine learning now, by CPU bound or RAM bound problems. So sometimes our data will not fit into memory, and that's kind of the classic case we've been dealing with here with Dask. And so up until this dotted line here, as long as our data fits into memory, we can typically use Scikit-Learn. And then along the y-axis here, we're bound by the CPU. And so say we have all of our data will fit into memory, but we have lots of computations from former CPU bound. We want to do parallel computations like parallel training or hyperparameter optimizations. We can use DaskML for that. And then of course, there's kind of this area where we're CPU bound and memory bound. We'll definitely need some form of distributed computing there. So going to go through Scikit-Learn really quick, just to familiarize ourselves. So Scikit-Learn has a really nice consistent API, has these estimators that all implement expected methods like fit and predict and score. They also have kind of standard attributes as well. We're just going to use the make classification data generator in Scikit-Learn. We're going to generate 10,000 samples and 4 features. I can't really see that. I'm going to move this over a bit. So essentially what we have here is a two-dimensional array with 4 columns and 10,000 rows. We also have some Ys, so we'll look at those. That's going to be our labels essentially. And now what we'll do is we'll use those X's and Y's to fit a support vector classifier. And so here we create the estimator object, initialize with a random state, and then call fit on that. Returns our estimator that has been fitted. And we can look at the support vectors. We can also check the scores. And check the accuracy essentially of our estimator that we've just trained. So that's what we're doing in a nutshell here with Scikit-Learn. Let's talk a little bit about hyperparameters. These are variables that are initialized with the estimator. They generally don't change for the training data. So here we're setting a couple of hyperparameters in the SVC and just calling the same functions we had before. We've set a really tiny C value here, and we'll see that whenever we score, our score is much worse because of that. So we can what this illustrates is by setting these hyperparameters, we can affect the accuracy of the model, and so these parameters become very important. Often you'll want to do what's called hyperparameter optimization, where you're experimenting with different values for these hyperparameters, and then training and doing the scoring and trying to figure out which set of hyperparameters will give you the best score. And so this is an example of a hyperparameter optimization called grid search CP in Scikit-Learn, and we'll just run that. And so essentially we're going to build up a parameter grid of 2 by 2 values, so 4 values total, and we're going to, the CV value here is just going to tell us how many estimators to train. And so you can see that that takes some time to compute, 22 seconds, but you'll notice that it is, when we kind of look at our graph here, this is a pretty trivialized to parallelized amount of work that we're going to do. Scikit-Learn has an internal parallel training mechanism based on job live. And so by specifying the number of jobs here, we can actually train in parallel to do our hyperparameter optimization. See, so we got 13 seconds, a little bit faster than 22, about half. So by using the job live parallelism, the job live parallelized library, we can train concurrently there. Turns out that job lib supports Dask as well for executing concurrent training. So I'm going to create client here real quick. Let everything connect up. So now what I'm going to do is train on a slightly different grid to perform grid search. And here,
too much, but just a heads up that we got a 2-minute warning.
Yep, this is the last thing I'm actually not going to run this last cell.
Perfect.
So I'm going to run with the job load parallel backend context, pass a parameter, letting it know that we're going to use Dask. This scatter was something that was required at one point. I don't think it's required anymore, though. I'm not sure. But now we're going to train using joblib in parallel, but we're going to use Dask as our backend. And this allows us to train or to perform our hyperparameter optimization on a larger grid, essentially. I didn't comment some of those that I could have, but just running locally, it would take too long and in the interest of time. So that is ML in a nutshell, real quick. So stop sharing.
Awesome. Thanks so much, Mike. And yeah, just kind of wrap up. Thanks everyone for attending today. We really appreciate your, like you said before, time and your attention during the tutorial. We know it was a long one. We can move the conversation to Slack if there are any follow-up questions. Otherwise, this will be available later for viewing.
All right. Yeah, just a final note as the host. Thank you guys for a great session. And a note for attendees. So the next thing is at 1:45 Central Time, the welcome stuff. So be there for that. And thanks very much for attending. Thank you guys for presenting.
Thanks for having us.
All right.
Bye, everyone.
So long.